Hello there and welcome to Learn When You Sleep. Tonight, we enter the silence that breathes, a journey into one of the strangest, most beautiful, and most unsettling ideas in all of modern science. Close your eyes and prepare to think about nothing. Not in the way you might think about nothing when your mind goes quiet on a slow afternoon. Not the comfortable blankness of an empty room or the stillness of a field at night. We are going to think about nothing in the way that physicists think about it, which turns out to be one of the most complicated, most surprising, and most profound subjects that human beings have ever encountered. Because here is the thing that changes everything. Nothing, as it turns out, is not nothing at all. Take a breath and let that thought settle for a moment. We live in a world that feels solid. The ground beneath you is real. The air in your lungs is real. The warmth of your blanket or your chair is real. Everything around you seems to be made of something. And the spaces between those somethings, the gaps between atoms, the emptiness between stars, the void between galaxies, seem to be made of nothing. That is how most of us picture the universe, matter here and empty space there. Things on one side and nothing on the other. It is a clean and comfortable picture. It is also, we now know, completely wrong. The empty spaces of the universe are not empty. They are alive with activity that we cannot see, cannot touch, and for a long time could not even imagine. The vacuum of space, that apparent nothingness between particles and planets and stars, is seething with invisible energy. It flickers with particles that appear from nowhere and vanish in an instant. It hums with fields that stretch across the cosmos and press outward against the very fabric of existence. And somewhere inside it, buried in the deepest structure of physical law, may be the key to understanding not only how the universe began, but how it might one day end. This is not science fiction. This is not a philosophical metaphor, though we will certainly explore those depths as well. This is physics. This is what the mathematics tells us, what experiments have confirmed, and what scientists are still trying to understand as you listen to these words tonight on Learn When You Sleep. The silence of empty space contains hidden music, and learning to hear it, even just learning to sense that it is there, changes the way the universe feels. Tonight, we will travel through this idea slowly, gently, letting each layer unfold before moving to the next. We will begin with the most basic question. What does it even mean to say that a space is empty? We will move from there into the strange world of quantum mechanics, where the rules of ordinary experience no longer apply. We will discover virtual particles, those ghostly flickers of matter that blink in and out of existence without ever quite arriving. We will look at the Casimir effect, one of the most beautiful experiments in all of science, where two metal plates placed close together in a near-perfect vacuum are pushed toward each other by the pressure of nothing. We will explore dark energy, that mysterious force making up most of the universe's total energy, which may be nothing more and nothing less than the energy of the vacuum itself. And finally, we will venture into territory that is as breathtaking as it is sobering. The possibility that the vacuum state of our universe is not the lowest energy state possible, that we may be living in a kind of cosmic bubble, and that somewhere, at some point, the bubble could collapse. But that is far from here. And this is not a story designed to frighten. It is a story designed to open, to show that even in the deepest silence, there is something, that even in the most perfect nothing, there is a kind of presence. That reality is more layered and more alive than the ordinary senses can detect. And that sitting with that knowledge, letting it breathe through you, can be one of the most calming and grounding experiences imaginable. So let us begin at the very beginning. Let us begin with the word empty. Think about what that word means to you. An empty room is one with no furniture, no people, no objects. An empty cup has no liquid inside it. An empty field has no crops, no structures, nothing cultivated. In each case, empty means the absence of the things we normally expect to find. It means cleared, bare, open. And there is something beautiful about emptiness in that ordinary sense. An empty room feels spacious. An empty afternoon feels free. An empty mind, for a moment, feels at rest. But physics asks a harder question. What would it mean for a space to be truly empty? Not empty of furniture or water or crops, but empty of everything. Empty of air, empty of dust, empty of radiation, empty of every particle, every field, every form of energy. Is such a thing possible? And if you could somehow create a space that contained absolutely nothing, what would you find there? For most of human history, the answer seemed obvious. If you removed everything from a space, you would find nothing. The ancient Greeks debated whether a true vacuum could exist at all, with some arguing that nature itself abhors emptiness and always finds a way to fill it. For centuries, philosophers and scientists wrestled with the idea, and when early experimenters began creating partial vacuums in the laboratory, the concept seemed to settle. A vacuum is a space from which matter has been removed. That is all. Beyond the matter, nothing remains. Then came the 20th century, and with it, quantum mechanics. And with quantum mechanics, the discovery that this comfortable picture was not just incomplete, but fundamentally mistaken, in ways so strange and so far-reaching that even the scientists who discovered them found it difficult to believe. What they found was this: even a perfect vacuum, a space emptied of every particle and every visible form of energy, is not truly empty. The vacuum has energy. The vacuum fluctuates. The vacuum is, in a very real and measurable sense, alive. This idea is called vacuum energy, and it is one of the most important, most mysterious, and most beautiful concepts in modern physics. It arises from quantum field theory, the framework that describes how particles and forces work at the smallest scales. And it tells us something extraordinary, that the ground state of the universe, the state it occupies when all energy has been stripped away, is not a state of peaceful stillness. It is a state of constant, irreducible, unstoppable activity. The vacuum hums, the vacuum flickers, the vacuum breathes. And that breath, as we will see over the course of this journey, may be the most important breath in the history of existence. It may be what holds atoms together. It may be what is pushing galaxies apart at this very moment. It may be what determines whether the universe as we know it continues forever, or transforms into something unimaginably different. But before we reach those heights, we should walk slowly through the foundations. We should understand the stage before we try to watch the play. We should ask not just what vacuum energy is, but why it exists at all, why the universe is built in such a way that even nothing must contain something. And that journey begins with a question about fields. Not fields of grass or fields of grain, but the invisible, omnipresent fields that physicists believe underlie all of reality. The stage on which every particle, every force, every event in the universe is performed. But for now, as we set off toward that idea, let us simply sit with what we have established so far. The empty space around you, the space inside this room, the space between the atoms of your hand, the space between the stars, is not empty. It is filled with something subtle, something invisible, something that science is only beginning to understand. And that something, that restless, flickering, breathing quality of the void, is what we are here to explore. Take another slow breath. Let the thought of a humming emptiness settle around you. And when you are ready, we will move to the next step, into the world of fields and into the deeper logic of why the universe is the way it is. The silence around you is not still. It never has been. And tonight, we are going to learn to hear it. Before we can understand why empty space is not empty, we need to understand one of the most important and most underappreciated ideas in all of physics: the idea of a field. This word gets used casually in conversations about magnetism, in descriptions of forces, in everyday language when we talk about a field of influence or a field of vision. But in physics, the word field has a precise and remarkable meaning. And once you understand what a field truly is, the strange behavior of the vacuum begins to make a different kind of sense. Not the ordinary common sense of objects and forces, but a deeper sense, the sense of something that is everywhere, always, and beneath everything. To begin this exploration, let us start with something familiar. Think about a magnet, not a huge industrial magnet, just a small one, the kind you might find holding a note to a refrigerator. If you hold that magnet in your hand and bring it close to a piece of iron, you feel something. A pull, a tug. The iron wants to move toward the magnet even before they touch. Something is acting across the space between them. Now here is the question that physicists eventually found themselves asking. What exactly is happening in that space? What is the medium through which the force travels? For a long time, the idea of action at a distance, of one object affecting another across a gap with nothing in between, troubled scientists deeply. Newton himself was uncomfortable with it, acknowledging that gravity seemed to act across vast distances with no visible mechanism. How could the sun pull on the Earth across 150 million kilometers of empty space? What was doing the pulling? The answer that physics arrived at, after centuries of investigation, is the field. A field is a physical quantity that has a value at every point in space. Not just near the magnet, not just between the magnet and the iron, but everywhere. The magnetic field of that small refrigerator magnet extends, in principle, across the entire universe. It weakens with distance, becoming vanishingly small, but it never truly reaches zero. Every point in space has a magnetic field value. That value might be almost nothing, almost undetectable, but it is there. This is a profound shift in how we picture reality. Instead of a universe made of objects surrounded by empty space, we begin to imagine a universe made of fields, with objects being, in some sense, disturbances or concentrations within those fields. The space between things is not empty. It is filled with the fields themselves, layers upon layers of invisible structure stretching in every direction, permeating every corner of existence. There are many fields in nature. There is the gravitational field, which gives every point in space a gravitational pull associated with the mass of nearby objects. There is the electromagnetic field, which combines electric and magnetic effects into a single unified framework. There is the Higgs field, about which we will say more later, which fills all of space and gives particles their mass. And in quantum field theory, the framework that combines quantum mechanics with the field picture, every type of fundamental particle is understood as an excitation of its own corresponding field. Let that idea breathe for a moment. Every particle in the universe, every electron, every photon, every quark, is not a tiny solid object floating through empty space. It is a vibration, a ripple, a disturbance in a field that stretches across the entirety of space and time. The electron is not a thing inside the electron field. The electron is what the electron field looks like when it is disturbed in a particular way, at a particular place, with a particular energy. This might sound abstract, almost uncomfortably so. but it is worth sitting with because it changes the texture of the universe. If every particle is a vibration in a field, and if those fields extend everywhere, then the fabric of existence is not made of discrete solid objects separated by gaps. It is made of something more like a continuous medium, an interconnected web of overlapping fields, each one stretching across all of space, each one capable of vibrating, each one capable of producing what we call particles when disturbed. And here is where the story becomes genuinely strange. Because quantum mechanics tells us something about these fields that classical physics never could have predicted. It tells us that the fields cannot be perfectly still. Even in a state with no particles, no radiation, no energy that we might normally count, the fields are still doing something. They are still fluctuating. They are still vibrating ever so slightly at every point in space, never stopping, never resting, never reaching a state of true, absolute silence. Why? To understand this, we need to take a small detour into one of the most important and most counterintuitive principles in all of physics. The principle that, in a very real sense, forbids the universe from ever being perfectly still. This is the Heisenberg uncertainty principle. And while you may have heard the name before, its implications go far deeper than most popular descriptions suggest. It is not simply a statement about the limitations of measurement, though that is one way to express it. It is a statement about the fundamental nature of reality. It says that certain pairs of physical properties, most famously position and momentum, but also energy and time, cannot both be precisely defined simultaneously. The more precisely you know one, the less precisely the other can be known. Not because our instruments are too clumsy, not because we have not built good enough devices, but because the universe itself does not allow both to be sharply defined at the same time. Think about what this means for a field. If a field were perfectly still, if it had exactly zero energy and exactly zero rate of change at every point, then we would know both its amplitude and its rate of change with perfect precision. But the uncertainty principle does not allow this. To know both the value of the field and the rate at which it is changing with perfect precision would violate the fundamental laws of quantum mechanics. Therefore, the field cannot be perfectly still. It must always be fluctuating, always jittering, always carrying some residual energy that cannot be removed no matter what you do. This residual energy is called the zero-point energy. And it is one of the most important concepts in all of quantum physics. Zero-point energy is the energy a quantum system must have even when it is in its lowest possible state. Even at absolute zero temperature, even when all thermal motion has been removed, even when the system is as cold and as quiet as it can possibly be, the zero-point energy remains. It is irreducible. It is unavoidable. It is a consequence not of heat or motion or any external cause, but of the deep structure of quantum mechanics itself. And because quantum field theory tells us that fields exist everywhere, and because each field carries zero-point energy, and because there are many fields, the conclusion follows with quiet inevitability. The vacuum, that empty space we thought contained nothing, is actually full of zero-point energy. It is the sum of the zero-point energies of all the quantum fields at all points in space. And that sum, when physicists try to calculate it, turns out to be very large indeed. Larger, in fact, than almost any other quantity in physics. But we will come to that puzzle in time. For now, let us stay with the picture that is emerging. The universe is made not of objects in empty space, but of fields that stretch everywhere. Those fields cannot be perfectly calm. They must always vibrate, always fluctuate, always carry a minimum irreducible energy. The vacuum is not the absence of fields. It is the state in which the fields are in their lowest energy configuration. And that configuration is not zero. It is not stillness. It is a constant, invisible, unavoidable hum. This hum has a name. It is called the quantum vacuum. And the energy associated with it, the zero-point energy of all the fields filling all of space, is called the vacuum energy. It is real. It can be measured. Its effects have been confirmed in experiments that are among the most precise ever conducted. And its implications, as we will see, extend from the smallest scales of particle physics to the largest scales of cosmology. From the interactions between atoms to the fate of the universe itself. Fields, then, are not just mathematical tools for describing forces. They are the substance of reality. They are what space is made of when you take away all the particles and all the energy that you can remove. What remains, what is always there, is the fields themselves. Vibrating, fluctuating, humming, invisible but real. Undetectable by the ordinary senses but measurable by the most sensitive instruments human beings have ever built. Think of the air in this room. You cannot see it. You cannot point to any particular molecule and watch it without sophisticated equipment. But you know it is there because of its effects, because it carries sound, because you breathe it, because you feel it when the wind moves. The quantum fields filling empty space are something like that, only far more subtle, far more fundamental, and present even where there is no air, no matter, no light. They are the bedrock of reality, the stage on which everything happens. And the stage, as it turns out, is not passive. The stage is not just a neutral backdrop on which particles perform their drama. The stage itself is alive. The stage itself contributes. The stage itself has energy, structure, and consequences that ripple outward into everything we observe. In the next part of our journey, we will move into quantum field theory more deeply, exploring what it means for reality to be made of vibrations, and beginning to see how those vibrations behave in the vacuum state. We will see how particles arise from fields, how interactions happen through the exchange of disturbances, and why this picture leads us inevitably toward the realization that the vacuum is not the end of the story. It is, in a very real sense, the beginning. For now, rest with the idea of the field. Feel the space around you differently, not as emptiness, but as a kind of invisible fabric. A fabric that reaches into every corner of the room, that extends through walls and floors and ceilings, that permeates the earth beneath you and the sky above you and the universe beyond that. A fabric that cannot be still, that is always, always moving, even when everything seems perfectly quiet. The stage is set. The fields are humming. And in the next layer of this story, we will begin to understand why. There is a picture of the universe that most of us carry from childhood, a picture so deeply embedded in the way we talk and think that it feels like simple common sense. In this picture, the universe is made of things. Tiny things, atoms and particles, that float through empty space, bump into each other, stick together, and in doing so build up everything we see. Stars and planets, trees and stones, hands and eyes. All of it assembled from a vast collection of microscopic building blocks, each one separate, each one distinct, each one a kind of miniature solid object. This picture is not wrong exactly. It is useful. It describes the world well enough for most purposes. But modern physics, specifically quantum field theory, has replaced this picture with something stranger and more beautiful. Something that requires us to let go of the idea of particles as solid objects and replace it with the idea of particles as events, as patterns, as vibrations in a continuous medium that fills all of space. To arrive at quantum field theory, it helps to understand what came before it. And what came before it was quantum mechanics. Quantum mechanics was developed in the 1920s by a remarkable group of physicists, and it overturned almost everything that classical physics had assumed about the behavior of small objects. Before quantum mechanics, physicists assumed that the universe operated on principles of continuity, that quantities like energy, momentum, and angular momentum could take any value along a smooth spectrum, that the position and velocity of a particle were always precisely defined, even if difficult to measure, that the universe, at its core, was deterministic. Know the state of everything now, and you could in principle calculate the state of everything at any future time. Quantum mechanics shattered all of this. It showed that energy comes in discrete packets called quanta, that the behavior of particles cannot be described in terms of precise positions and velocities, but only in terms of probabilities, that measuring one property of a system can instantly affect another property, no matter how far apart those properties are, that the universe at its smallest scales is fundamentally, irreducibly, irreversibly probabilistic. These were shocking discoveries. Even Einstein, who contributed fundamentally to the development of quantum theory, never fully accepted its probabilistic nature, famously insisting that God does not play dice with the universe. And yet the experiments confirmed quantum mechanics again and again, to a precision that no other theory in the history of science has matched. But quantum mechanics, as originally formulated, had a problem. It was not compatible with special relativity. Special relativity, Einstein's earlier theory, had shown that space and time are not separate absolute quantities, but are woven together into a single fabric called spacetime. It had shown that nothing can travel faster than light, and that the laws of physics must look the same to all observers moving at constant velocities. Quantum mechanics, in its original form, treated space and time differently, and it did not respect these relativistic symmetries in the way that a fundamental theory needed to. The solution was quantum field theory. Developed through the 1930s and 1940s by physicists including Paul Dirac, Werner Heisenberg, Wolfgang Pauli, Julian Schwinger, Richard Feynman, and Shinichiro Tominaga, quantum field theory married quantum mechanics with special relativity into a single consistent framework. And in doing so, it completely changed the picture of what particles are. In quantum field theory, the basic objects of reality are not particles. They are fields. Fields that stretch across all of spacetime, that have a value at every point, and that can vibrate and fluctuate in complex patterns. What we call particles are not independent objects floating through these fields. They are excitations of the fields. They are quantized vibrations. They are, in a precise mathematical sense, the smallest possible disturbance that a given field can support. Let us make this more concrete with an example. Consider light. We know from experience that light behaves sometimes like a wave and sometimes like a particle. This is the famous wave-particle duality that lies at the heart of quantum mechanics. In quantum field theory, this apparent contradiction is resolved. Light is described by the electromagnetic field. The electromagnetic field fills all of space. When the electromagnetic field vibrates, when it undergoes an oscillation of a particular energy and frequency, we call that vibration a photon. The photon is not a tiny ball flying through space. The photon is what happens when the electromagnetic field is excited in a particular way. It is the field itself, rippling. The same is true for electrons. There is an electron field that fills all of space. When that field is excited with enough energy in a particular region, we observe what we call an electron. The electron is a stable vibration of the electron field. When two electrons interact, repelling each other through electromagnetic force, what is happening in this framework is that the electron fields of both electrons are interacting with the electromagnetic field, exchanging vibrations back and forth. The force between the electrons is mediated by the exchange of photons, the quantized vibrations of the electromagnetic field. This picture applies to every particle we know. Every quark has a corresponding quark field. Every neutrino has a neutrino field. Every force is mediated by its own field and its own corresponding particle. The strong nuclear force that holds atomic nuclei together is mediated by gluons, excitations of the gluon field. The weak nuclear force that governs radioactive decay is mediated by W and Z bosons. And the gravitational force, though not fully incorporated into quantum field theory, is believed to be mediated by gravitons, excitations of the gravitational field. The universe, in this picture, is an orchestra. Not an orchestra of solid instruments sitting in empty air, but an orchestra made entirely of sound. The fields are the music, the particles are the notes, and the silence between the notes, the vacuum state of all these fields, is not absence. It is the hum of all the instruments before the music begins, the readiness, the potential, the irreducible activity of a system that cannot quite come to rest. Now, here is where the concept of the vacuum becomes central. In quantum field theory, the vacuum is defined as the lowest energy state of all the fields. It is the state in which there are no particles, no radiation, no excitations of any kind that we would normally count as energy. But as we discussed when we talked about zero-point energy, the fields in the vacuum state are not still. They cannot be still. The uncertainty principle forbids it. Because each field is a quantum system, and because quantum systems cannot occupy a state of perfect stillness without violating the uncertainty principle, every field in the vacuum is constantly undergoing small, rapid, unavoidable fluctuations. These fluctuations are not the same as particles. They are not stable excitations of the field. They are more like trembling, like the quivering of a string that cannot quite stop vibrating. And they carry energy. Real energy, present throughout all of space, at every point, at every moment. The sum of all this zero-point energy from all the fields at all points in space is what we call the vacuum energy. And here is where physicists encountered one of the most famous and most troubling problems in all of modern science. When they tried to calculate the vacuum energy using the mathematics of quantum field theory, they got an answer. And that answer was not a small number. It was not even a large number. It was, depending on how you did the calculation, infinite. Or, if you cut off the calculation at the point where quantum gravity presumably takes over, it was a finite number, but a number so enormous that it made almost no physical sense. This is called the vacuum energy problem, or sometimes the cosmological constant problem. And it is one of the deepest unsolved puzzles in physics. We will explore it in much more detail later in our journey, when we talk about dark energy and the accelerating expansion of the universe. But for now, it is enough to register that the vacuum energy is not zero, that this is not a theoretical curiosity but a measurable, physical reality, and that its implications are still being worked out by the brightest minds in physics. What quantum field theory gives us, then, is a world made of vibrations. Not the vibrations of solid things trembling in empty space, but vibrations that are, in some fundamental sense, all there is. The fields are real, The particles are patterns in the fields. The vacuum is the ground state of all the fields, humming with zero-point energy, flickering with fluctuations that are too small and too fast to see but too real and too consequential to ignore. And this world of vibrations has consequences that reach far beyond the mathematics. It means that the boundary between something and nothing is not sharp. It means that the vacuum is not the opposite of reality, but a kind of reality in its own right. A minimal, irreducible, quietly active version of reality that underlies everything else. The basement of existence, always occupied, never quite dark. One of the most beautiful things about quantum field theory is how it unifies the concepts of particle and wave. Before quantum mechanics, physicists treated particles and waves as completely different kinds of thing. A particle is a localized object. A wave is a spread-out disturbance. The strange experiments of the early 20th century showed that electrons and photons seemed to behave like both, and this was deeply puzzling. Quantum field theory dissolves the puzzle by showing that both behaviors arise from the same underlying reality, the field. When the field has a definite energy, it behaves like a particle. When it spreads out and interferes with itself, it behaves like a wave. Both behaviors are aspects of the same thing, seen from different angles, described at different levels of resolution. This unification is profoundly satisfying. It suggests that the apparent duality of the world, the tension between the particle view and the wave view, is not a fundamental feature of nature but an artifact of our limited perspective. From the field perspective, there is no contradiction. There is only the field vibrating in different ways, producing different effects, but always one thing. As you let this picture settle into your mind tonight, try to feel the space around you differently. Instead of imagining empty air between objects, imagine a continuous fabric of fields, a fabric so fine that no ordinary instrument can detect it directly, a fabric that permeates everything, that passes through walls and through you, that has been here since the very early moments of the universe and will be here long after every star has burned out. A fabric that cannot be still, that trembles constantly, that carries energy even in the deepest quiet. This is the world that quantum field theory describes. A world not of things in space, but of vibrations in fields. A world where the vacuum is not empty but teeming with invisible activity. A world where even the most perfect silence contains, at its deepest level, an irreducible, inescapable, beautiful hum. And from that hum, as we will see in the next part of our journey, arise some of the strangest and most wonderful phenomena that physics has ever described. The ghosts of particles that appear and disappear faster than can be directly observed. The phantom visitors to our universe who carry out their brief existence and vanish before we can quite catch them. They are called virtual particles, and they are, in a profound sense, what the silence is made of. There is a law in nature that is not like the other laws. Most laws of physics tell you what things do. They describe how objects move, how forces act, how energy is conserved, how time flows. But the Heisenberg uncertainty principle does something different. It does not describe what things do. It describes what things cannot be. It is a law that sets limits on reality itself, limits that are not the result of ignorance or imprecision or the limitations of our instruments, but limits that are woven into the very fabric of existence. And understanding this principle, really understanding it, is essential to understanding why the vacuum is alive with energy, why empty space cannot be truly empty, why the universe at its foundations is in a state of perpetual, unavoidable, irreducible motion. Werner Heisenberg was 25 years old in 1927 when he first formulated the uncertainty principle that would bear his name. He was sitting on a small island in the North Sea, isolated from colleagues and distractions, trying to work through the mathematical foundations of the new quantum mechanics that he and his colleagues had been developing. What he arrived at was not a practical observation about measurement difficulty, not a statement about how hard it is to observe tiny things without disturbing them. It was something deeper, a fundamental incompatibility built into the structure of quantum mechanics, a constraint on what can be simultaneously defined, a statement about the nature of reality at its most basic level. The uncertainty principle, in its most common formulation, states that the more precisely you know the position of a particle, the less precisely you can know its momentum, and vice versa. Position and momentum are what physicists call conjugate variables, and the product of the uncertainties in their values can never be smaller than a particular tiny constant, known as Planck's constant divided by 2. This is not a practical limitation. You cannot engineer your way around it. You cannot build a better detector. You cannot develop a more sensitive method. The uncertainty is not in your instrument. It is in the particle. The particle does not have a definite position and a definite momentum at the same time. This is not because we do not know them. It is because there are no such definite values to know. Let that land gently. The particle, before it is measured, does not have a precise location. It exists in a kind of smear, a probability cloud, a range of possible positions with different probabilities. When you measure it, you find it somewhere. But the act of finding it, of pinning it to a specific location, forces its momentum to become spread out and uncertain. The more you nail down where it is, the less you can know about how fast it is moving and in what direction. The two properties trade off against each other in a dance that can never be resolved, a fundamental complementarity written into the mathematics of quantum mechanics. Now, there is another version of the uncertainty principle that is even more directly relevant to our story tonight. It involves not position and momentum, but energy and time. The energy uncertainty principle states that the more precisely you try to define the energy of a system during a very short time interval, the less precisely that energy can be determined. Or to put it differently, a system can spontaneously borrow energy from nowhere, violating conservation of energy, as long as it pays that energy back quickly enough. The shorter the time the energy is borrowed, the larger the amount that can be borrowed. The larger the amount borrowed, the shorter the time it can be kept. This sounds, on first hearing, like magic, or fraud, or some kind of cosmic loophole, but it is a prediction of quantum mechanics that has been confirmed by experiment after experiment with extraordinary precision. Nature really does allow this. Energy really can fluctuate. The books do not have to balance at every instant, only over sufficiently long time intervals. In the very short term, on the timescales of quantum fluctuations, energy can appear and disappear, popping in and out of existence like bubbles in a pot of water, never staying long enough to violate the fundamental conservation laws in any measurable way, but always present, always active, always doing something. This is the mechanism behind the quantum fluctuations of the vacuum. The fields filling all of space cannot sit perfectly still at zero energy, because if they did, we would know both their exact value and their exact rate of change, violating the uncertainty principle. Instead, they fluctuate. They tremble. They borrow energy for the briefest possible moments and then return it, over and over ceaselessly everywhere at every point in space, at every moment in time. Think of a vast, perfectly still body of water. In classical physics, such a thing could exist. A lake's surface perfectly flat, perfectly calm, with every molecule sitting exactly in place. In quantum physics, this is impossible. Even at absolute zero temperature, even with no wind and no disturbance of any kind, the water molecules would still be jittering, vibrating at their lowest possible energy level. The zero-point energy of the molecular vibrations would ensure that perfect stillness is forever out of reach. The lake can be calm. The lake can be very nearly still, but it cannot be perfectly, absolutely, completely still. The uncertainty principle will not allow it. And what is true for a lake is true for the quantum fields filling all of space. They are as quiet as they can be in the vacuum state. All the excitations that correspond to real particles have been removed. All the energy that can be removed has been removed, but the fields are still there, and they are still fluctuating. The vacuum is the state of maximum quiet, but it is not a state of silence. It is a state of irreducible, minimal, perpetual vibration. There is something philosophically remarkable about this. The universe at its lowest energy state is not a state of rest. It is a state of restlessness. The ground floor of existence is not a quiet basement, but a room that cannot stop humming, a space that cannot stop trembling, a void that cannot stop being in some sense something. The uncertainty principle does not just limit our knowledge of the universe. It actively shapes the universe itself, preventing it from ever reaching the absolute zero of activity, ensuring that even in the most perfect vacuum, something is always happening. This idea has a resonance that goes beyond physics. It suggests that becoming truly nothing, reaching a state of absolute zero activity, is not just difficult but impossible. At the deepest level of physical reality, existence resists erasure. Energy resists being completely zero. Fields resist being perfectly flat. Reality has, built into it, a kind of minimum vitality, a floor below which it cannot sink, a baseline of activity that no process, no cooling, no emptying can remove. Now let us think about what this looks like in practice. Imagine a small region of space that is as empty as it can possibly be. No particles, no radiation, no thermal energy of any kind. What is happening in that region? According to quantum field theory, the fields filling that region are fluctuating. Not visibly, not in a way that could be detected by any simple instrument. But the quantum mechanical fluctuations are there, the zero-point oscillations of every field that exists in nature. Every now and then, one of these fluctuations will be energetic enough to produce what looks, for a fleeting instant, like a pair of particles. A particle and its antiparticle, appearing together out of the fluctuation, and then disappearing back into it before they can be directly detected. These are the virtual particles that we will explore in the next part of our journey. But even between those brief appearances, even in the tiny intervals between fluctuations, the fields are there. They are vibrating. They are carrying energy. The vacuum is alive in the quietest possible way, but alive nonetheless. And this aliveness has consequences that reach from the very small to the very large, from the structure of atoms to the shape of the universe. It is worth taking a moment to appreciate how strange this is, even for physicists who have spent their careers working with these ideas. The notion that nothingness cannot be truly nothing, that the absence of everything still contains something, that reality has a minimum irreducible activity built into its foundations. This is not a comfortable or familiar idea. It contradicts almost every intuition we have about the meaning of emptiness. It requires us to revise, at the most fundamental level, what we think empty means. Empty, in the quantum sense, does not mean absent. It does not mean still. It does not mean inactive. Empty in the quantum sense means as quiet as quantum mechanics will allow. And as quantum mechanics makes clear, that is not very quiet at all. The quietest possible state of all the fields in the universe is a state of constant, invisible, irreducible fluctuation. The most perfect vacuum is a bustling, trembling, humming sea of quantum activity. As you rest with this idea, let it change the texture of the space around you. The air between you and the nearest wall is not just air. It is a region filled with quantum fields, each one vibrating at its 0 point, each one contributing to the background hum of the vacuum. The space inside your body, the gaps between your atoms, the distances between the electrons in your cells and the nuclei they orbit, all of it filled with the same fields, all of it contributing to the same irreducible energy. You are not surrounded by nothing. You are surrounded by the minimum possible something, and that minimum is not zero. The Heisenberg uncertainty principle is often presented as a limitation, as a frustrating barrier that prevents us from knowing everything we might want to know about the universe. But there is another way to see it. It is the principle that prevents the universe from becoming nothing. It is the rule that ensures the fields will always vibrate, that the vacuum will always hum, that even in the deepest emptiness there will always be this irreducible, inescapable, fundamental activity. Without the uncertainty principle, in a world described by classical mechanics alone, the vacuum could be perfectly still. There would be no 0 point energy, no virtual particles, no vacuum fluctuations. The silence would be absolute. But in our universe, the uncertainty principle reigns. And because of it, the silence is never absolute. The vacuum is never truly empty. The nothing never quite becomes nothing. And from this irreducible something, all the richness and complexity and wonder of physical reality ultimately springs. The uncertainty principle, in this light, is not a limitation. It is a generative force. It is the reason the vacuum hums. It is the reason virtual particles flicker into existence. It is the reason the Casimir force pushes metal plates together in an empty room. It is the reason dark energy fills the cosmos with an outward pressure. It is, in a deep sense, the reason anything exists at all. So when you lie quietly tonight, and the room feels still, and the world feels calm, remember that beneath that stillness is a deeper restlessness. A restlessness that has been there since the beginning of time and will be there long after everything we know has changed. The uncertainty principle is always at work, ensuring that the vacuum is always active, ensuring that nothing cannot be nothing, ensuring that even in the most perfect silence, something is always, gently, inescapably, humming. Every language has words for things that are between categories. Words for states that are neither fully one thing nor fully another. The moment between sleeping and waking. The color between blue and green. The feeling between joy and grief that does not have a name but that everyone has experienced. Physics has such a thing too. A class of entity that is neither quite real nor quite absent. Neither fully a particle nor simply nothing. Something that exists only in the gap between certainty and uncertainty. That flickers into brief being at the edge of what is measurable. That shapes the world in countless ways without ever quite arriving in it. These are virtual particles. And they are among the most fascinating, most misunderstood, and most important inhabitants of the quantum vacuum. To understand what a virtual particle is, we first need to revisit the relationship between particles and energy. In quantum field theory, as we discussed, a real particle is a stable excitation of a quantum field. It has a definite energy and a definite momentum. and these are related to its mass in a precise way described by Einstein's special relativity. When we say that an electron has a mass of a certain value, what we mean is that the electron field, when it is excited in the stable way that produces a real electron, carries energy and momentum in a specific ratio. This relationship between energy, momentum, and mass is called being on shell. A real particle is always on shell. It always satisfies this fundamental relationship. Virtual particles, by contrast, are off shell. They are excitations of a quantum field that do not satisfy the usual energy-momentum-mass relationship. They can have, temporarily, the wrong ratio of energy to momentum for their mass. They can appear to have more or less energy than their mass would dictate. They can borrow from the vacuum, using the energy-time uncertainty principle to exist briefly in states that a real particle never could. And because they exist only for very short times, the uncertainty principle allows them to get away with this. The books do not have to balance in the short term. The energy borrowed must be returned, but not immediately. And in that narrow window, virtual particles can act. They can mediate forces. They can create effects. They can leave measurable traces in the world. The most important role of virtual particles is as the carriers of forces between real particles. When two electrons repel each other, what is actually happening, in the language of quantum field theory, is that they are exchanging virtual photons. One electron emits a virtual photon, a fluctuation of the electromagnetic field. The other electron absorbs it. The momentum carried by this virtual photon is what we experience as the electromagnetic force between the electrons. The virtual photon never exists as a real, detectable, on-shell photon. It is an internal process, a temporary fluctuation, an off-shell excitation that does its work and disappears without ever being directly observable. This picture of forces as the exchange of virtual particles is one of the great insights of 20th century physics. It explains not just electromagnetism, but all the fundamental forces. The strong nuclear force that binds quarks together into protons and neutrons is mediated by virtual gluons. The weak nuclear force that governs radioactive decay is mediated by virtual W and Z bosons. Gravity is believed to be mediated by virtual gravitons, though a complete quantum theory of gravity does not yet exist. All the forces of nature, according to this picture, are the result of matter constantly exchanging virtual particles, constantly sending out and absorbing these off-shell fluctuations of the underlying fields. In the vacuum, with no real particles present, virtual particles still appear. Not because there are real particles exchanging them, but because the vacuum fluctuations of the fields, those unavoidable zero-point oscillations we discussed, can produce pairs of virtual particles that momentarily pop into existence and then annihilate each other. A virtual electron and a virtual positron, a virtual quark and a virtual antiquark, a pair of virtual photons. These pairs appear together, exist for the briefest possible moment, and then recombine and vanish. They never accumulate. They never become detectable in the direct sense. But they are constantly happening, and their presence has real, measurable effects on the world around them. One of the most beautiful ways to see the effect of virtual particles is through a phenomenon called the Lamb shift. In 1947, the physicist Willis Lamb made a precise measurement of the energy levels of the hydrogen atom and found a tiny discrepancy from the predictions of the then current theory. Two energy levels that should have been exactly the same were actually slightly different. The difference was incredibly small, a shift of about 1,000th of a percent, but it was real and reproducible. The explanation, worked out shortly afterward, was virtual particles. The electron in a hydrogen atom is not alone. Even in the vacuum state, virtual particles constantly appear and disappear around it, flickering into existence and out again. These virtual pairs, and the resulting fluctuations of the electromagnetic field, perturb the electron's energy in a way that depends on which energy level the electron is in. The two levels that should be the same are not the same because the virtual particle environment around the electron at each level is slightly different. The Lamb shift is direct experimental evidence that virtual particles are real, that they have real effects, and that the quantum vacuum is not a passive backdrop, but an active participant in physical processes. An even more famous example of the reality of vacuum fluctuations, one we will spend considerable time on in the next part of our journey, is the Casimir effect. Two uncharged metal plates placed close together in a near-perfect vacuum attract each other, not because of any classical force between them, but because the presence of the plates changes the pattern of virtual particles that can exist in the space between them versus outside them. The vacuum pushes the plates together with a force that has been precisely measured and precisely predicted by quantum field theory. It is one of the most direct demonstrations imaginable that the empty space between the plates is not empty at all, but filled with this invisible sea of virtual activity. Virtual particles also play a role in one of the most dramatic processes in physics, Hawking radiation. In 1974, the physicist Stephen Hawking showed that black holes are not truly black. They radiate. The mechanism, as Hawking described it, involves virtual particle pairs appearing near the event horizon of the black hole. Normally, a virtual pair appears and almost immediately recombines. But near an event horizon, the intense gravitational field can pull the pair apart before they can recombine, causing one particle to fall into the black hole while the other escapes into space as real radiation. The black hole loses mass in the process, and over an enormous timescale, it eventually evaporates entirely. This result, which combined quantum mechanics and general relativity in a new way, is considered one of the most profound theoretical discoveries of the 20th century, and it all hinges on the reality of virtual particles and vacuum fluctuations. It is important to be clear about what virtual particles are not. They are not simply a mathematical bookkeeping device with no physical meaning. But they are also not tiny solid objects flying around in space like microscopic billiard balls. The language of particles, when applied to virtual particles, is an approximation, a visualization tool, a way of making sense of the underlying mathematics. The deeper reality is the fluctuation of the quantum field itself, the jittering zero-point oscillations of the vacuum. Virtual particles are what those oscillations look like when we try to describe them in terms of particles. They are, in a sense, the vocabulary we use to tell the story of the vacuum. There is something poetic about this. The world is described, at its most fundamental level, not in terms of things, but in terms of fluctuations. Not in terms of solid objects, but in terms of what happens between objects. The forces that hold matter together, the energetic humming of the vacuum, the evaporation of black holes, all of these phenomena arise from these ghostly, transient, off-shell visitors to reality. Virtual particles are not quite there. They are never quite here, but they shape the world as surely as anything that is. This might prompt a philosophical question, and it is a good one. If a virtual particle is never directly detected, If it always vanishes before it can be directly observed, in what sense is it real? This is not a simple question. It touches on deep issues about the nature of physical reality and what we mean by saying something exists. One answer is operational. A virtual particle is real if its effects are real. And the effects of virtual particles are absolutely real. The Lamb shift is real. The Casimir force is real. Hawking radiation is theoretically real and consistent with everything we know about quantum mechanics and general relativity. The effects are real, and if those effects can only be explained by the presence of these transient fluctuations, then the fluctuations themselves deserve to be called real in any meaningful sense. Another way to think about it is to step back from the language of particles entirely. The vacuum is not filled with tiny particles appearing and disappearing. The vacuum is filled with a quantum field that is fluctuating at its 0 point level. The fluctuations are real. The energy is real. The effects on nearby matter are real. We call certain aspects of these fluctuations virtual particles because that language is convenient, because it gives us an intuitive picture, because it maps onto our everyday concept of things. But the underlying reality is the field, always vibrating, always active, never quite still. As you settle into this tonight, consider what the virtual particle picture does to our notion of emptiness. The vacuum is not a place where nothing happens. It is a place where an extraordinary variety of things happen, all of them too fast and too fleeting to observe directly, all of them canceling each other out in the long run, but all of them contributing to the background energy of the vacuum state, all of them leaving their marks on the real particles that exist among them. The empty space in this room, the gap between you and the nearest wall, is teeming with these transient events. At this very moment, as you breathe and rest, pairs of virtual particles are appearing and disappearing in the air around you and in the space between your atoms. They are not disturbing you. They are not pulling you in any particular direction. Their effects average out to something we experience as the ordinary background state of space. But they are there. They have always been there. They are what the quiet of the vacuum actually sounds like, if you could hear it, if you could zoom in close enough, fast enough. A vast, invisible symphony of appearances and disappearances. Ghostly dancers in an empty room. Real enough to measure, brief enough to vanish, permanent enough in their collective effect to shape the deepest structures of the universe. This is what the silence contains. This is what the vacuum is made of. And in the next part of our journey, we will see how this invisible activity was first directly measured in one of the most elegant and surprising experiments in the history of science. Two metal plates, empty space, and a force that should not be there. Rest for a moment with the idea of the virtual world. A world of flickering appearances. A world of borrowed moments. A world where nothing is ever quite nothing, and where the most fleeting ghosts leave the deepest marks. There is a particular kind of beauty in science that arrives not through grand theories or sweeping discoveries, but through a single clean experiment that makes the invisible visible. An experiment so elegant in its design that the result feels almost like a magic trick, except that the magic is real, and the trick is performed by the universe itself, using the hidden machinery of the quantum vacuum. The Casimir effect is exactly this kind of experiment. It is one of the most direct, most unambiguous demonstrations that the vacuum is not empty, that virtual particles are not merely theoretical conveniences, and that the 0 point energy of empty space is a physical reality with measurable consequences. And to understand it, all you need is two metal plates, a very good vacuum, and a willingness to be surprised by nothingness. The story begins in 1948, in the Netherlands, at the Philips Research Laboratories in Eindhoven. A Dutch physicist named Hendrik Casimir was working on a problem related to the stability of colloid particles, tiny droplets suspended in a fluid. He was trying to understand why these particles sometimes stuck together even when they should have been electrically neutral and therefore should not have attracted each other. Working through the mathematics of van der Waals forces, the weak attractive forces between neutral molecules, he found himself led to a startling and unexpected conclusion. Two perfectly flat, perfectly conducting, uncharged metal plates placed close together in a vacuum should experience an attractive force between them, a force that arises not from any charge or field in the conventional sense, but from the quantum vacuum itself. Let us think carefully about why this should be so. Imagine two large, flat, perfectly conducting metal plates placed parallel to each other, separated by a very small gap. Outside the plates, stretching in all directions, is empty space, the quantum vacuum with all its fluctuating fields and virtual particle activity. Inside the gap between the plates, there is also empty space, also the quantum vacuum, also the same fluctuating fields. At first glance, it seems like nothing should happen. The vacuum is the same everywhere. The plates are neutral. There are no charges, no currents, no forces in any ordinary sense. But here is the key. The metal plates impose a boundary condition on the electromagnetic field. Because the plates are conductors, the electric field inside the conductor is zero. The electromagnetic field at the surface of each plate must satisfy this boundary condition. And this means that only certain modes of the electromagnetic field can exist in the space between the plates. Specifically, only those modes whose wavelengths fit exactly into the gap between the plates can exist there. It is like fitting standing waves between two walls. Only the waves that have a node at each wall, that fit an integer number of half wavelengths into the space, can survive. All other modes are excluded. Outside the plates, in the open vacuum, there is no such restriction. Every possible mode of the electromagnetic field can exist. Every wavelength, every frequency, every pattern of fluctuation is permitted. The outside vacuum is the full, unconstrained quantum vacuum with its complete spectrum of zero-point fluctuations. Now here is the consequence. The energy of the vacuum between the plates is less than the energy of the vacuum outside the plates. Because some modes are excluded from the gap, the vacuum inside is quieter, in a sense, than the vacuum outside. The outside has more zero-point energy per unit volume than the inside, and this difference in energy creates a pressure. The outside vacuum, with its richer spectrum of fluctuations, pushes inward on the plates. The inside vacuum, with its restricted spectrum, pushes outward less effectively. The net result is a force pushing the two plates toward each other, a force that arises purely from the difference in vacuum fluctuations inside and outside the gap. A force from nothing, in the most literal sense imaginable. This is the mechanism behind the Casimir force. And Casimir worked out the mathematics precisely enough to make a quantitative prediction. For two large, perfectly flat, perfectly conducting plates separated by a distance of 1/100th of a millimeter, the force per unit area should be about 1/1,000,000th of atmospheric pressure. This is not a large force by everyday standards, but it is a specific, calculable, testable prediction. And it depends on no free parameters, no adjustable constants, no unknowns. It follows directly from the structure of quantum electrodynamics, the quantum field theory of electromagnetism. For decades after Casimir's prediction, the force was accepted theoretically but difficult to measure precisely. The technical challenges are formidable. The plates must be very flat, very smooth, and very close together. Any roughness, any dust, any vibration, any stray charge on the surfaces can mask the tiny Casimir force. The gap between the plates must be controlled to within nanometers. The whole apparatus must be shielded from electromagnetic interference and thermal noise. For many years, experimental attempts produced results that were consistent with the prediction, but not precise enough to constitute a rigorous confirmation. Then, in 1997, the physicist Steve Lamoureau at the University of Washington performed a much more precise measurement, using a torsional pendulum whose deflection could be measured to extraordinary accuracy. His results agreed with the theoretical prediction of Casimir to within about 5%. For such a delicate measurement of such a subtle effect, this was considered excellent agreement. Subsequent experiments by other groups improved the precision further, and today the Casimir effect has been measured with errors of less than 1%. The agreement with quantum field theory is essentially perfect. The Casimir effect is important for many reasons. But perhaps the most profound is what it tells us about the nature of the vacuum. The force is not mediated by any particle that we can detect. It does not involve any classical field. It is not caused by charges or currents or magnets. It is caused by the difference in the quantum vacuum fluctuations on either side of the plates. It is caused by the constraint that the metal surfaces impose on the spectrum of virtual photons that can exist in the gap. It is, in a very direct sense, caused by the vacuum itself. The vacuum is doing something. The vacuum is pushing. The empty space between the plates is exerting a real, measurable, reproducible force. And this means the vacuum has energy, real energy, energy that can do work. Energy that moves things. If the vacuum energy were truly zero, if empty space contained absolutely nothing, then the Casimir force would be zero. The fact that it is not zero is direct experimental proof that the vacuum is not empty. It is, in a quantifiable sense, full. The Casimir effect also has implications that reach beyond fundamental physics into engineering. As technology advances and devices become smaller, reaching the nanometer scale, the Casimir force becomes increasingly relevant. At distances of a few nanometers, the Casimir force can be comparable in magnitude to other forces acting on tiny mechanical components. It can cause surfaces to stick together, a phenomenon called stiction, which is a serious problem in the design of microelectromechanical systems. Understanding and controlling the Casimir force is therefore not just a matter of theoretical curiosity, but a practical engineering challenge for the designers of the smallest machines. There have also been theoretical proposals, speculative but not ridiculous, for using the Casimir effect as a source of energy. If you could somehow extract energy from the vacuum by manipulating the boundary conditions that determine which vacuum modes are allowed in a given space, you might be able to tap into the enormous reservoir of zero-point energy that quantum field theory tells us fills all of space. This idea, known as vacuum energy extraction, faces formidable theoretical and practical obstacles, and most physicists are skeptical that it will ever be realized. But the very fact that it can be seriously discussed is a measure of how far our understanding of the vacuum has come. The vacuum has energy. That energy is real, and the question of whether it can be accessed, even in principle, is a legitimate scientific question. There is a variation of the Casimir effect, sometimes called the dynamical Casimir effect, that is even more striking. In the ordinary Casimir effect, the plates are stationary, and the force arises from the static difference in vacuum modes inside and outside the gap. In the dynamical Casimir effect, one of the plates is moved very rapidly, accelerating at speeds comparable to a significant fraction of the speed of light. Under these conditions, the rapidly changing boundary conditions can actually convert virtual photons, those vacuum fluctuations that exist only transiently, into real photons, stable excitations of the electromagnetic field that can be detected. The vacuum, stirred by the moving plate, produces real light from nothing. This effect was predicted theoretically in the 1970s and first observed experimentally in 2011, using a superconducting circuit that could simulate the effect of a moving mirror. The creation of real photons from the vacuum is perhaps the most direct visualization of the virtual particle sea that we have available. It shows that the vacuum is not just flickering passively. It can be stimulated. It can be made to yield real particles. It is responsive to disturbance in ways that make its energy content undeniable. The Casimir effect in all its forms is a window into the quantum vacuum, a way of seeing the invisible, of measuring the unmeasurable, of touching the untouchable. Two metal plates and the force of nothing between them. It is one of the most philosophically resonant experiments in the history of science, because it tells us, with the precision of measurement and the rigor of mathematics, that the silence between things is not silence at all, that the space between surfaces is alive with fluctuations, that nothing is never quite nothing, that the very act of creating a boundary, of saying here is one side and there is the other, already changes what the vacuum is doing. The Casimir effect reminds us that emptiness is relational. The vacuum between the plates is different from the vacuum outside, not because the physics is different, but because the boundaries have changed what configurations are possible. The vacuum is sensitive to context. It responds to geometry. It notices the presence of boundaries and adjusts itself accordingly. And that adjustment creates a force, a real force, a force you can measure, a force you can use to push a tiny pendulum, a force from the quantum breathing of empty space. As you rest with this tonight, let the image of those two metal plates stay with you. They are close together, parallel, facing each other across a tiny gap. Between them, the vacuum is quieter than it is outside them. Its modes are restricted. Its virtual photons are constrained to fit between the boundaries. And because of that constraint, because of that difference in the richness of the vacuum on either side, the plates are drawn toward each other. Gently, measurably, inevitably. The silence between the plates is pulling them together. The nothing is doing something. And that is perhaps the most beautiful sentence in all of physics. When physicists try to calculate the energy of the vacuum, they encounter a number so strange, so large, and so seemingly disconnected from observation that it has been called the worst prediction in the history of physics. Not because the theory is wrong, not because the mathematics is poorly done, but because the mathematics, done carefully and correctly, produces an answer that conflicts with what we observe in a way that is so extreme, so breathtaking in its scale, that it has challenged the best minds in theoretical physics for decades without a satisfying resolution. This conflict is called the cosmological constant problem, and it begins with a very simple question. What is the energy density of empty space? To approach this question, we need to think about what it means to add up the zero-point energies of all the quantum fields filling all of space. Recall that each quantum field, everywhere in space, at every point, carries a minimum irreducible energy called its zero-point energy. This energy arises because the uncertainty principle prevents the field from being perfectly still. The field vibrates constantly, and this vibration has energy. The vacuum energy is the sum of all these zero-point energies, from all the fields, at all the points, at all the frequencies. Now, quantum field theory is a framework that works at scales we understand. It describes the behavior of particles and fields at the energies accessible to our particle accelerators. But it does not tell us what happens at arbitrarily high energies, at arbitrarily small scales. At some point, when distances become small enough and energies become large enough, quantum mechanics and gravity must both be important simultaneously. This regime, near the Planck scale, a length of about 10 to the negative 35 meters, requires a theory of quantum gravity that we do not yet have. Below that scale, our current theories are not reliable, so physicists make a practical choice. They calculate the vacuum energy by summing the zero-point energies of all modes of the quantum fields, but only up to the Planck scale. They cut off the sum at the point where the theory is expected to break down. This is a reasonable thing to do. It gives a finite answer rather than an infinite one. And that finite answer is a specific, calculable number. The number is approximately 10 to the power of 97 kilograms per cubic meter. That is a 1 followed by 97 zeros in kilograms per cubic meter. This is an almost incomprehensibly large energy density. It is vastly, absurdly, colossally larger than anything we observe in the universe. The actual observed energy density of the universe is roughly 10 to the power of negative 27 kilograms per cubic meter. The theoretical prediction and the observation differ by a factor of about 10 to the power of 124. That is a 1 followed by 124 zeros. No other prediction in physics is this wrong. No other theory in science produces a result this far from observation. And this is not a situation where the experiments are uncertain or the observations are noisy. The observation is robust. The universe does not have the energy density that quantum field theory naively predicts for the vacuum. The universe is almost perfectly close to having zero vacuum energy density, or at least a vacuum energy density that is 124 orders of magnitude smaller than the theoretical prediction. This discrepancy is the cosmological constant problem. And it is one of the deepest, most frustrating, most important unsolved problems in all of theoretical physics. We will return to it when we discuss dark energy, because the actual observed vacuum energy density is not quite zero. There is a small, positive, measured value that we call the cosmological constant or dark energy. But that value is so incredibly close to zero compared to what the theory predicts that the discrepancy is essentially unchanged. The predicted value is enormous. The observed value is tiny. Something is canceling almost all of the theoretical vacuum energy, leaving only this minuscule residue. We do not know what is doing the canceling. We do not understand why the cancellation is so nearly perfect. This is one of the great mysteries of modern science. To appreciate the scale of this problem, it helps to use an analogy. Imagine you are trying to balance two very large numbers that you have calculated independently. The first number is 10 to the power of 124. The second number must also be this large, because their difference, whatever remains after you subtract one from the other, must equal an extremely precise and tiny value. The precision required is like measuring the length of the observable universe and getting an answer that is accurate to within the width of a single proton. Any tiny error in either number would produce a result wildly different from what is observed. The two numbers must cancel to more than 100 decimal places. This level of precision does not happen by accident in physics. It usually signals that there is a deep reason, a symmetry or a principle, that is forcing the cancellation. But in the case of the vacuum energy, no such principle has been found. One class of proposed solutions involves a symmetry called supersymmetry. Supersymmetry is a theoretical extension of the standard model of particle physics that pairs every known particle with a partner particle of a different type. Fermions, particles with half-integer spin like electrons and quarks, are paired with bosons, particles with integer spin, and vice versa. One of the attractive features of supersymmetry is that it naturally cancels large quantum corrections to certain quantities, because the contributions from fermions and bosons tend to have opposite signs. In a perfectly supersymmetric universe, the vacuum energy from all the bosonic fields would exactly cancel the vacuum energy from all the fermionic fields, giving a total vacuum energy of precisely zero. But we do not live in a perfectly supersymmetric universe. No supersymmetric partner particles have been discovered at the energies accessible to our particle accelerators. If supersymmetry exists, it must be broken at some energy scale, meaning the masses of the partner particles are different from those of the known particles. And when supersymmetry is broken, the cancellation is no longer perfect. A residual vacuum energy remains. The question is whether this residual energy is close enough to the observed value to count as an explanation. So far, the answer appears to be no. The residual vacuum energy from broken supersymmetry is still much larger than what is observed. Another approach invokes the anthropic principle. This is the idea that the vacuum energy has the value it does, at least in part, because if it were very different, we would not be here to observe it. If the vacuum energy were much larger and positive, the universe would have expanded so rapidly after the Big Bang that matter would have been scattered before it could clump together into galaxies, stars, planets, and observers. If the vacuum energy were large and negative, the universe would have quickly collapsed back on itself, again preventing the formation of complex structures. The observed value of the vacuum energy is one of the few values consistent with the existence of observers who can measure it. This argument, associated most prominently with the physicist Steven Weinberg, who made a precise prediction of the cosmological constant using anthropic reasoning in 1987, is controversial. Many physicists find it unsatisfying as a fundamental explanation. It seems to explain the value of a physical constant by appeal to the fact that we observe it, which feels circular. But Weinberg's prediction was made before the accelerating expansion of the universe was discovered, and his predicted range turned out to contain the observed value. Whether this counts as a genuine success of anthropic reasoning or a coincidence is still debated. There is a deeper philosophical dimension to the vacuum energy problem that is worth sitting with. The vacuum energy is not something we calculated incorrectly. Quantum field theory, which predicts the large vacuum energy, is one of the most precisely tested theories in the history of science. Its predictions for the behavior of particles and forces are confirmed to extraordinary accuracy. The Casimir effect, the Lamb shift, the magnetic moment of the electron, all are explained by quantum field theory with breathtaking precision. The theory works. And part of the theory is the large vacuum energy. Yet the universe does not seem to have this large vacuum energy. Or rather, something cancels it almost perfectly. We know the result of the cancellation because we can measure the small residual vacuum energy that powers the acceleration of the universe. But we do not know what is doing the canceling. We have a theory that works brilliantly for almost everything and fails catastrophically for this one number. And that failure is not a small discrepancy. It is a discrepancy of 124 orders of magnitude. This situation is humbling. It reminds us that however successful our theories are, there are depths of nature that we have not yet plumbed. There is something about the vacuum, about the relationship between quantum mechanics and gravity, about the way the universe chose its ground state, that we do not understand. The sea beneath everything has a depth we cannot yet measure. And yet, sitting with this mystery is not uncomfortable. The vacuum energy problem is not a failure of science. It is a signpost pointing toward new physics, toward discoveries that have not yet been made. Every great unsolved problem in physics has eventually led to a revolution in understanding. The ultraviolet catastrophe of classical physics led to quantum mechanics. The incompatibility of Newton's gravity with electromagnetism led to special relativity. The vacuum energy problem may one day point the way toward a quantum theory of gravity, or toward a deeper understanding of the structure of space-time, or toward a new principle that constrains the vacuum energy to its observed value. The sea beneath everything is real. Its energy is real. The measurement of that energy, as the cosmological constant, as dark energy, as the tiny but non-zero residue that drives the acceleration of the universe, is one of the great observational achievements of modern cosmology. The mystery of why it is so small, so nearly zero compared to the theoretical prediction, is one of the great open questions of modern physics. And both of these things, the measured reality and the theoretical mystery, point in the same direction. Toward a universe in which the vacuum is not passive, not inert, not simply the absence of things. The vacuum is a medium. The vacuum has properties. The vacuum has energy. The vacuum shapes the universe. And understanding it is one of the central tasks of 21st century physics. Rest for a moment with the image of this sea beneath everything. An invisible ocean of zero-point energy extending through all of space, present beneath every particle, every force, every structure in the universe, too large by the theory's own prediction to match what we observe, too small by all ordinary reckoning to seem like anything at all, and yet real enough and non-zero enough to be pushing the galaxies apart at this very moment. That is what we will explore next. The dark energy, the silence that pushes. The vacuum energy residue that is quietly, steadily, inexorably reshaping the geometry of the universe. The discovery that empty space is not empty did not arrive in a single dramatic moment. It was not like the fall of an apple that supposedly inspired Newton, or the flash of insight that Archimedes was said to have experienced in his bath. It was a slower realization, built up through decades of experiment, through the accumulation of small discrepancies and unexpected measurements, through the gradual acceptance of a picture of reality that contradicted almost every classical intuition. And it unfolded along two parallel tracks. One track was the theoretical development of quantum mechanics and quantum field theory, which predicted the vacuum fluctuations and virtual particles we have been discussing. The other track was the observational history of cosmology, which eventually revealed that the universe itself is expanding in a way that cannot be explained without invoking the energy of the vacuum. Tonight, let us walk slowly through both of these histories, not rushing, letting each step take its proper time, because the story of how we learned that nothing is something is one of the most remarkable stories in the history of human thought. The theoretical track begins in the early 20th century with the birth of quantum mechanics. One of the first hints that the vacuum might not be empty came from a phenomenon that was puzzling and important: blackbody radiation. A blackbody is an idealized object that absorbs all radiation that falls on it and emits radiation based only on its temperature. In the late 19th century, physicists had developed a classical theory of blackbody radiation, but when they tried to calculate how much radiation a blackbody should emit at different wavelengths, they got an absurd result. According to the classical calculation, a blackbody should emit infinite amounts of energy at short wavelengths. The prediction was so wildly wrong that it was called the ultraviolet catastrophe. Max Planck solved this problem in 1900 by proposing that electromagnetic radiation is emitted in discrete packets, quanta, rather than continuously. This was the beginning of quantum theory. And one of the consequences of Planck's quantization was that even at zero temperature, even when a system has given up all the energy it can, there remains a minimum irreducible quantum of energy in each mode of vibration. This was the first glimpse of the zero-point energy. Even at absolute zero, systems still vibrate. Even the coldest possible state retains this irreducible quantum buzz. This idea was developed further in the 1920s as the full framework of quantum mechanics was constructed. The zero-point energy of the harmonic oscillator, one of the simplest quantum systems, was worked out precisely and shown to be non-zero. Any quantum system that is confined, any system that has a definite minimum energy, must have this residual activity. And when quantum mechanics was extended to fields, when quantum field theory was developed in the late 1920s and 1930s, the zero-point energy of the fields immediately implied that the vacuum, the state with no real particles present, still contained energy. Infinite energy, in fact, without some cutoff, which was one of the first signs that quantum field theory had deep problems to solve. The experimental confirmations of vacuum effects came in several stages. We have already discussed the Lamb shift, discovered in 1947, which showed that virtual vacuum fluctuations modify the energy levels of the hydrogen atom in measurable ways. This was among the first direct experimental evidence that the vacuum was doing something physically real. It was not just a theoretical artifact. It changed the behavior of real atoms in ways that could be precisely measured and precisely calculated. Then came the Casimir effect, predicted in 1948 and eventually measured with high precision. Then came the discovery of the anomalous magnetic moment of the electron, a tiny deviation from the classical prediction of how strongly an electron responds to a magnetic field, which arises from the interaction of the electron with the virtual particles in the vacuum around it. The agreement between the quantum field theory prediction of this anomalous magnetic moment and its experimental measurement is one of the most precise agreements in all of science, accurate to more than 10 decimal places. Every one of those decimal places is a confirmation that the vacuum is real, that virtual particles are real, and that quantum field theory correctly describes the interaction of matter with the invisible sea of fluctuations that surrounds it. But these confirmations, precise as they are, all operated at the level of individual particles and atoms. The cosmic implications of the vacuum energy remained murky for a long time. The cosmological track of the discovery begins much earlier, with Einstein. In 1915, Einstein completed his theory of general relativity, the modern description of gravity. General relativity describes gravity not as a force but as the curvature of spacetime, caused by the presence of mass and energy. Massive objects curve the spacetime around them, and other objects move along the curved paths that result. When Einstein applied his equations to the universe as a whole, he found that a static universe, one that neither expands nor contracts, was impossible without an additional term in the equations. Left to itself, the gravity of all the matter in the universe would cause it to collapse inward. Einstein added a term to his equations, which he called the cosmological constant and denoted by the Greek letter lambda, to counteract the gravitational collapse and allow for a static universe. But in 1929, Edwin Hubble discovered that the universe is not static, it is expanding. Distant galaxies are moving away from us, and the farther they are, the faster they are receding. This expansion, extrapolated backward in time, pointed to the universe having a hot, dense beginning, what we now call the Big Bang. With the discovery of expansion, Einstein felt that the cosmological constant was no longer needed, and he famously called it his greatest blunder, a term he had introduced unnecessarily to save a picture of the universe that turned out to be wrong. For decades after Hubble's discovery, the cosmological constant was largely abandoned. The universe was expanding. The question was simply how the expansion was evolving. Since gravity is attractive, the expansion should be slowing down over time. The mutual gravitational pull of all the matter in the universe gradually decelerating the outward motion of the galaxies. The rate of deceleration would depend on the total amount of matter, and this became one of the central questions of cosmology. Was there enough matter to eventually halt the expansion and reverse it, leading to a big crunch? Or would the universe expand forever, thinning and cooling into a dark and empty future? Then came 1998, and with it, one of the most surprising discoveries in the history of science. Two independent teams of astronomers, one led by Saul Perlmutter and another led by Brian Schmidt and Adam Rees, were using a particular type of supernova, the type Ia supernovae that serve as standard candles for measuring cosmic distances, to map the expansion history of the universe. Their goal was to measure the rate at which the expansion was slowing down. They expected to find deceleration, the gradual breaking of the expansion under the influence of gravity. What they found instead was the opposite. The expansion of the universe is not slowing down, it is speeding up. The galaxies are not just moving apart, they are accelerating away from each other. Something is pushing them, spreading them apart at an ever-increasing rate. Something is overcoming the gravitational pull of all the matter in the universe and driving the expansion to accelerate. This discovery won Perlmutter, Schmidt, and Rees the Nobel Prize in Physics in 2011. And it completely changed our picture of the universe. The something that is driving the accelerating expansion was given the name dark energy. And the simplest and most natural explanation for dark energy, though not the only one, is exactly the vacuum energy that quantum field theory predicts. A constant energy density associated with empty space itself, a cosmological constant with a small positive value, enough to accelerate the expansion, but not so large as to tear the universe apart before structures could form. So the discovery that the vacuum is not empty arrived from two directions simultaneously. From the smallest scales, the anomalous magnetic moment of the electron, the Lamb shift, the Casimir effect, all pointed to a vacuum teeming with quantum fluctuations. From the largest scales, the accelerating expansion of the universe pointed to a vacuum with a small but non-zero energy density. The two discoveries are, almost certainly, connected. The dark energy that drives cosmic acceleration is, in the most natural interpretation, the energy of the vacuum itself. The quantum fluctuations that produce the Casimir effect and shift the energy levels of hydrogen are, at least qualitatively, the same phenomenon as the dark energy reshaping the universe. The quantitative connection remains deeply mysterious because the theoretical prediction of the vacuum energy is so enormously larger than the measured value of dark energy. But the qualitative connection seems hard to deny. The vacuum has energy. We know it from atomic spectroscopy. We know it from the Casimir effect. We know it from the accelerating expansion of the universe. We know it from multiple independent lines of evidence, all pointing to the same conclusion. Empty space is not empty. The vacuum is alive with energy. And that energy shapes everything from the smallest atom to the largest structure in the universe. The history of this discovery is, in a way, the history of science learning to see what it previously could not, to see the invisible, to measure the absence, to detect the presence of something where common sense insisted there was nothing. Each step required new mathematics, new instruments, new ways of asking questions about the world. And each step revealed a universe more surprising, more subtle, and more alive than the previous step had suggested. To trace this history is to feel a kind of vertigo, the intellectual vertigo of realizing that the universe is not what it appears, that the most ordinary thing in the world, empty space, the gap between objects, the darkness between stars, is in fact one of the most extraordinary things in the universe. Full of energy, full of fluctuations, full of virtual particles, full of dark energy, full, in some deep sense, of the potential for everything that exists. And we learned all of this not by accepting it intuitively, not because it fit our picture of the world, but because the experiments demanded it, because the numbers refused to behave, because the universe kept insisting that the old picture of empty space was wrong. And when we finally listened to what the universe was telling us, we found not emptiness, but the most remarkable thing imaginable. A silence that breathes, a void that hums, a nothing that is, in every measurable sense, something. The universe is getting bigger, not in the way a balloon grows when you blow air into it, where the rubber stretches and the air inside rearranges itself. The universe is getting bigger in a more fundamental way. The space between galaxies is growing. Not because the galaxies are flying apart through space, but because the space itself is expanding, carrying the galaxies with it the way raisins in a rising loaf of bread are carried apart not by their own motion, but by the growth of the dough between them. This expansion has been happening since the Big Bang, for nearly 14 billion years. And for most of that time, it was assumed that the expansion was gradually slowing down, that the gravitational pull of all the matter in the universe was acting as a brake, decelerating the outward rush of the galaxies, even if not quite enough to stop it entirely. But as we have seen, the discovery of dark energy showed that this assumption was wrong. The expansion is accelerating, and this acceleration is driven by the energy of the vacuum. Think about what this means for the relationship between the vacuum and the universe as a whole. In classical physics, space is a container. It is a stage on which things happen, but it does not participate in the action. In general relativity, space is a fabric. It curves and stretches in response to mass and energy. But in the universe we inhabit, space is even more than that. Space is a source of energy. Every cubic meter of empty space, regardless of where it is, contains a certain amount of vacuum energy. And as the universe expands, as more space is created between the galaxies, the total amount of vacuum energy in the universe increases. This is a profound shift in our understanding of the cosmic balance sheet. In a universe made only of matter, the density of matter decreases as the universe expands. The same amount of matter is spread over a larger and larger volume, but the density of vacuum energy is constant. It does not thin out. It does not weaken. It is a property of space itself. And because there is more and more space, the influence of vacuum energy becomes stronger and stronger over time relative to the gravity of matter. This is why the expansion is accelerating. We have entered an era of cosmic history in which the vacuum is the dominant force in the universe. The galaxies are being pushed apart by the irreducible energy of the nothingness between them. The vacuum is winning the tug of war against gravity, and the fate of the universe is being determined not by the things inside it, but by the silence that surrounds them. This is the dark energy. This is the cosmological constant. This is the vacuum energy residue that survived the early moments of the Big Bang and is now driving the universe toward an ever thinner, ever colder, ever lonelier future. And yet, even in that darkness, the vacuum will still be humming. Even when the galaxies are too far apart to see each other, even when the stars have burned out and the black holes have evaporated, the fields will still be fluctuating. The zero-point energy will still be there. The silence will still be breathing, because as we have learned, the silence is never absolute. The nothing never quite becomes nothing. And that is the deepest secret that the vacuum has revealed to us so far. Then came 1998 and the discovery we discussed in the previous part of our journey. The expansion is not slowing down. It is speeding up. And the something responsible for this acceleration, the invisible, mysterious, pervasive energy that is overcoming gravity and pushing the universe apart at an ever greater rate, is what we call dark energy. Dark energy is strange. It is strange in a way that goes beyond the ordinary strangeness of quantum mechanics or relativity. It is strange because it behaves unlike anything else we have ever encountered. All the forms of energy and matter that we know, light, gas, dust, dark matter, everything, contribute to the gravitational attraction that tends to pull things together. More matter means more gravity means more deceleration. That is how ordinary physics works. Dark energy does the opposite. Dark energy causes the expansion to accelerate. It acts like a repulsive gravity. It pushes outward rather than pulling inward. It makes the universe expand faster and faster rather than slower and slower. How can energy repel? The key is not just the energy itself, but the pressure associated with it. In general relativity, both energy and pressure contribute to the gravitational effect of a substance. Ordinary matter has positive pressure, like the pressure of a gas, and this positive pressure contributes to gravitational attraction. But dark energy, if it is the energy of the vacuum, has a peculiar property. Its pressure is negative, equal in magnitude to its energy density but opposite in sign. This negative pressure is the key to everything. When you have an energy density accompanied by a negative pressure, the combined effect in general relativity is repulsive rather than attractive. The dark energy pushes outward on the fabric of space-time, causing it to expand at an accelerating rate. This property of negative pressure is not just a theoretical assumption. It follows directly from the quantum field theory picture of the vacuum. The vacuum energy, by its very nature, has a specific relationship between its energy density and its pressure. It satisfies what physicists call an equation of state, where the pressure equals -1 times the energy density. This is the equation of state of a cosmological constant. A constant energy density that fills all of space uniformly. That does not dilute as the universe expands. That is the same everywhere at all times. and that carries this distinctive signature of negative pressure. Current measurements of the expansion rate of the universe, when combined with observations of the cosmic microwave background and the large-scale structure of the universe, tell us that dark energy makes up approximately 68% of the total energy content of the universe. This is remarkable. Most of the universe, by energy, is this invisible, mysterious, vacuum-like energy that we do not fully understand. Ordinary matter, the atoms and molecules that make up stars and planets and you and everything you have ever seen, accounts for only about 5% of the total. Dark matter, the invisible gravitating substance that makes up the bulk of matter in the universe, accounts for about 27%. Dark energy dominates everything. The universe is mostly made of something we discovered only 25 years ago and still cannot explain at a fundamental level. The simplest model for dark energy is the cosmological constant, the lambda that Einstein introduced and then abandoned. In this model, dark energy is simply the energy of the vacuum, constant, uniform, and with a fixed equation of state. This model fits all current observations remarkably well. The accelerating expansion, the age of the universe, the geometry of space-time, the pattern of galaxies on large scales, all are consistent with a cosmological constant with a specific, tiny positive value. But simplicity is not the same as understanding. The cosmological constant fits the data, but it does not explain why the vacuum energy has this particular value, rather than the much larger value predicted by quantum field theory. It does not explain why it is not zero, which might at least be explained by some symmetry. And it does not explain the so-called coincidence problem, the puzzling fact that the density of dark energy and the density of matter are roughly comparable today, even though their ratio changes dramatically as the universe evolves. If dark energy has always been constant and matter density has been decreasing as the universe expands, why are they similar in magnitude right now, at this particular epoch of cosmic history? This seems like a remarkable coincidence, and coincidences of this kind in physics often signal that something deeper is going on. Some physicists propose that dark energy is not a cosmological constant but something that changes over time. A dynamic field, sometimes called quintessence, that fills space and has an energy density that evolves as the universe evolves. In quintessence models, the dark energy is not truly constant but varies slowly, its equation of state deviating slightly from -1. Current observations cannot clearly distinguish between a cosmological constant and slowly varying dark energy, but future surveys may be able to. Several major astronomical projects are underway or planned, specifically designed to measure the properties of dark energy with sufficient precision to test whether it is truly constant or whether it evolves with time. The implications of dark energy for the future of the universe are dramatic. If dark energy remains constant, as the cosmological constant picture suggests, then the universe will continue to expand forever at an ever-accelerating rate. Over time, the galaxies outside our local group will recede beyond our event horizon, their light never able to reach us again. The universe will become progressively darker and lonelier. Stars will burn out. Black holes will eventually evaporate. And in the far future, separated by timescales that make the current age of the universe seem like a brief instant, the universe will approach a cold, dark, nearly empty state dominated by the ever-present energy of the vacuum. This is sometimes called the Big Freeze or the heat death of the universe. Not a dramatic end, not a collapse or an explosion, but a gradual fading. A long, slow, irreversible spreading out, the galaxies dispersing, the stars going dark, the black holes evaporating, and the vacuum energy, the dark energy, remaining, because the vacuum energy, by its very nature, does not dilute with expansion. It stays constant. In a universe of maximum emptiness, the vacuum energy would still be there, the last remaining form of energy in a universe from which everything else has been drained. But some models of dark energy predict a more dramatic ending. If the dark energy equation of state deviates from -1 in a particular direction, if the dark energy becomes more negative than -1 as time goes on, then the dark energy density would not remain constant but would actually increase as the universe expands. More space means more dark energy, which means more expansion, which means more space, which means more dark energy. A runaway process. In these models, the accelerating expansion would eventually become so violent that it would overcome not just the gravity between galaxies, but the gravity holding galaxies together, then the electromagnetic forces holding molecules and atoms together, then the nuclear forces holding atomic nuclei together, and finally, the quantum mechanical forces holding particles themselves together. Everything would be torn apart in a final catastrophic event called the Big Rip. Current observations suggest that the dark energy equation of state is very close to -1, consistent with a cosmological constant and inconsistent with the extreme models that predict a Big Rip. But the observations are not precise enough to rule out a slow drift in the equation of state that might eventually lead to a big rip in the far future. We are, in a sense, still learning the character of the dark energy, still trying to determine whether it is constant and eternal or evolving and potentially dangerous. There is something deeply humbling about dark energy. We live in a universe that is 68% something we do not understand. We can measure its effects with great precision. We can describe its behavior with mathematical models. We can constrain its properties with careful observations. But we do not know what it fundamentally is. We do not know where it comes from. We do not know why it has the value it has. And we do not know with certainty what it will do to the universe in the future. The silence that pushes is real. We have measured it. It has changed the universe. It is changing the universe right now, as you listen to these words, as the galaxies beyond our local group recede from us a tiny bit faster than they were yesterday. The vacuum energy, the dark energy, the cosmological constant, whatever we choose to call it, is the dominant form of energy in the universe. And yet it is the most mysterious, the least understood, the most stubbornly opaque to our theoretical framework. It is the silence at the heart of the universe's expansion. It is the pressure of emptiness against the fabric of space. It is the hum of the vacuum, amplified to cosmic scale, shaping the destiny of everything that exists. And perhaps the most remarkable thing about it is that it was there all along. Not hiding, not lurking, not waiting to be discovered. Just present, just doing what it does. Quietly, uniformly, without drama, pushing. And we, tiny inhabitants of a small planet orbiting an ordinary star, looked carefully enough at the light of distant exploding stars and realized that the silence was pushing us apart. That the nothing between galaxies was the most powerful thing in the universe. That realization, quiet and slow as it was in arriving, is one of the great achievements of human curiosity. And it points toward even deeper questions about the nature of the vacuum, about whether our vacuum is the only possible vacuum, about what it would mean if the vacuum were to change. Those are the questions we turn to next, as we go deeper into the most unsettling and most beautiful territory in all of physics. Of all the numbers in physics, there may be none more mysterious than the cosmological constant. It is a number so small that writing it out in decimal form requires placing more than 120 zeros after the decimal point before reaching the first non-zero digit. It is a number so precisely tuned that if it were even slightly larger, the universe would have expanded too rapidly for galaxies to form. If it were slightly smaller and negative, the universe would have collapsed back on itself before stars could ignite. It sits at a value so extraordinarily close to zero, and yet so precisely non-zero, that it seems to demand an explanation that physics has not yet been able to provide. It is Einstein's great puzzle, though Einstein himself never knew it in this form. And sitting with it, really sitting with it, is one of the most philosophically vertiginous experiences that modern science has to offer. Let us begin with the history, because the cosmological constant has a rich and strange biography that mirrors the development of cosmology itself. Einstein introduced the cosmological constant in 1917, 2 years after completing general relativity, when he applied his field equations to the universe as a whole. General relativity describes how matter and energy curve spacetime, and how the curvature of spacetime determines how matter moves. When Einstein applied these equations to a universe filled uniformly with matter, he found that it was unstable. A static universe, one that neither expanded nor contracted, was impossible unless he added an additional term to his equations. This term was the cosmological constant, represented by the Greek letter lambda. A constant energy density associated with empty space itself, spread uniformly throughout the universe, with a value chosen precisely to counterbalance the gravitational attraction of matter and allow the universe to remain static. Einstein was not happy with this addition. It seemed arbitrary. It had no physical motivation beyond the desire to obtain a static solution. He included it because the observations of the time seemed to require a static universe, but he recognized it as an inelegant move, a term inserted by hand into the equations to get the desired result. Then came Hubble's 1929 discovery that the universe is expanding, and Einstein abandoned the cosmological constant, calling it, in various accounts, his greatest blunder, not because it was mathematically wrong, but because it was unnecessary. A static universe did not need to be saved. The universe was not static. It was expanding. The cosmological constant was a solution to a problem that did not exist. For the next several decades, the cosmological constant was largely ignored, though it was never completely absent from theoretical discussions. Some physicists kept it in their equations as a possible term that could in principle take any value, including zero. Observationally, the dominant view was that it was zero, or so close to zero as to be undetectable. This seemed reasonable. There was no observed effect that required it. And zero is a much more natural value for a constant than some tiny but non-zero number, because zero often signals a symmetry or a conservation law that sets a quantity exactly to nothing. Then came the vacuum energy problem. When quantum field theory was developed and its implications for the vacuum were worked out, physicists realized that the vacuum should have an energy density. And this vacuum energy density is, from the perspective of general relativity, exactly what the cosmological constant describes. A constant energy density filling all of space, contributing to the curvature of space-time. The cosmological constant and the vacuum energy are, in Einstein's framework, the same thing. They are two ways of describing the same physical quantity. This connection made the problem worse, not better. Because quantum field theory predicted that the vacuum energy density should be enormously large. And if the vacuum energy is equivalent to the cosmological constant, then the cosmological constant should also be enormously large. But observations showed it was essentially zero. The discrepancy between the theoretical prediction and the observational constraint was the 124 orders of magnitude that we have already discussed. This is the cosmological constant problem. And it is, in the words of many physicists, the most severe fine-tuning problem in all of science. Fine-tuning refers to situations where a physical parameter must be adjusted to an extraordinary precision to match observation. In this case, the vacuum energy predicted by quantum field theory must be cancelled to more than 100 decimal places by some other contribution to the cosmological constant. The cancellation must be so perfect that the residual value is 10 to the power of minus 124 times the theoretical value. No known symmetry, no known principle, no known mechanism produces this cancellation naturally. It has to be there. The universe would not exist in its current form without it. But we have no idea why it is there. One attempt to understand the problem involves quantum corrections. In quantum field theory, the physical value of any parameter is not simply its bare value, but the sum of its bare value and all the quantum corrections to it. These corrections come from the interactions of the parameter with virtual particles and vacuum fluctuations. For the cosmological constant, the quantum corrections are enormous and positive. For the observed value to be small, the bare cosmological constant must be enormous and negative, and the sum of the two enormous numbers must equal the tiny observed value. This requires a cancellation between two independently calculated numbers that is accurate to more than 100 decimal places. Physicists sometimes call this a naturalness problem. A theory is natural if the values of its parameters do not require extreme fine-tuning. The cosmological constant problem represents a spectacular failure of naturalness. There is no known reason why the cosmological constant should take such a tiny value. It is unnatural in the most extreme sense that the word can have in physics. Yet the universe exists. The galaxies formed, the stars ignited, life emerged. All of this happened because the cosmological constant is extraordinarily small. If it were not, if the cancellation were slightly less perfect, the universe would look nothing like it does. It would either have expanded too fast and too violently for matter to clump, or it would have collapsed before anything interesting could happen. This brings us to the anthropic reasoning we touched on earlier. The physicist Steven Weinberg argued, in a remarkable paper published in 1987, that the cosmological constant must be small, not because of any deep theoretical reason, but because if it were large, we would not be here to observe it. He went further and made a quantitative prediction. The cosmological constant can be at most large enough to have a modest effect on the formation of galaxies. If it were any larger, galaxies would not have formed and observers would not exist. Weinberg predicted, on these anthropic grounds, that if the cosmological constant is non-zero, it should be on the order of the density of matter at the time of galaxy formation. This prediction, made 11 years before the accelerating expansion was discovered, turned out to be remarkably accurate. The observed value of the cosmological constant is indeed on the order of the matter density, within the range that allows structures to form. Weinberg's anthropic prediction has been cited as one of the most successful applications of anthropic reasoning in physics. But not everyone is satisfied. Many physicists feel that anthropic arguments are not real explanations. They do not tell you why the cosmological constant has a specific value. They only tell you that the value must be compatible with observers existing. This is a necessary condition, not a sufficient one, and it leaves open the question of what mechanism actually sets the value. The most ambitious attempt to go beyond anthropic reasoning involves the landscape of string theory. String theory, one of the leading candidates for a fundamental theory of physics, predicts a vast number of possible universes, each with different values of the physical constants, including the cosmological constant. This landscape of possibilities, which some estimates place at 10 to the power of 500 possible universes, could in principle explain why our universe has such a tiny cosmological constant. In a landscape with such an enormous number of possibilities, a small fraction will have cosmological constants in the range compatible with galaxy formation. And if all these universes exist, perhaps in a vast multiverse, then we would inevitably find ourselves in one of the rare ones with a small cosmological constant. This is a profound and controversial idea. It shifts the question from why does our universe have this cosmological constant to why do we find ourselves in this particular universe among many. But it requires accepting a multiverse that may be fundamentally unobservable, which makes many physicists uncomfortable. A theory that cannot be tested is not obviously science. And the string landscape is so vast, so diverse, and so difficult to navigate mathematically that making specific testable predictions from it has proven very challenging. What the cosmological constant problem ultimately reveals is the depth of our ignorance about the vacuum. We know the vacuum has energy. We can measure it. We can calculate, at least approximately, what it should be from quantum field theory. We can compare the prediction to the observation and find a catastrophic discrepancy. And then we are stuck. We do not know how to reconcile the microscopic prediction with the macroscopic observation. We do not know what principle is responsible for the near-perfect cancellation. We do not know whether the cosmological constant is truly constant or whether it might evolve. And yet this ignorance is not the end of the story. It is the beginning of a question that the next generation of physics will have to answer. The cosmological constant is a clue. It is telling us something about the nature of the vacuum, about the relationship between quantum mechanics and gravity, about the deepest structure of physical law. We have not yet decoded the message, but the message is there, written in the most precise measurement in cosmology and in the most severe fine-tuning problem in all of science. Einstein called the cosmological constant his greatest blunder, but he was wrong about that, too, in an ironic way. The cosmological constant was not a blunder at all. It was a prescient recognition that the equations of general relativity allow for something extraordinary, a constant energy of empty space, a background hum that permeates the universe, a term that, in the right form and with the right value, can drive the expansion of the universe to accelerate. Einstein was right to include it. He was right that it was strange. He was wrong to call it a mistake. Because the cosmological constant, as we now understand it, is one of the most important quantities in all of physics, and it is still waiting for the explanation that will one day transform our understanding of the vacuum, of space-time, and of the nature of reality itself. Rest for a moment with the number, the cosmological constant, tiny beyond imagining, precisely tuned beyond any known principle, observed with extraordinary precision, predicted catastrophically wrong by quantum field theory. and yet somehow exactly the right value to allow galaxies and stars and planets and you. The puzzle of the cosmological constant is a puzzle about why we exist, and we do not yet know the answer. But knowing that we do not know is itself a form of knowledge. It is the honest, humbling, inspiring recognition that the universe is still mysterious, that the vacuum is still speaking to us in a language we have not quite learned to read, and that the most ordinary thing in the universe, empty space, contains within it one of the deepest unresolved questions in the history of human thought. There is a particular kind of strangeness that comes not from discovering something alien and incomprehensible, but from discovering that something familiar, something you thought you understood completely, has been behaving in a way you never suspected. The expansion of the universe was not a new idea in 1998. Astronomers had known for nearly 70 years that the universe was getting bigger, that the galaxies were receding from each other, that space itself was stretching in every direction. This was established, accepted, part of the standard cosmological model. What was not established, what no one expected, was that this expansion was accelerating, that the universe was not just getting bigger, but getting bigger faster and faster with every passing moment. To understand why the acceleration was so surprising, we need to think about what everyone expected to find. In a universe filled with matter, gravity acts on large scales as a decelerating force. Every galaxy exerts a gravitational pull on every other galaxy. This pull acts against the expansion, trying to slow it down, trying to bring the galaxies back together. Whether the expansion would eventually stop and reverse, leading to a big crunch, or whether it would slow but never quite stop, leading to infinite expansion, depended on the total density of matter in the universe. If the density was above a critical value, the universe would recollapse. Below it, the expansion would continue forever, but always decelerating. No one seriously considered the possibility of acceleration. Acceleration would require a form of energy with negative pressure, a form of energy that acts repulsively rather than attractively on the large-scale structure of space-time. Nothing in the physics of matter or radiation has this property. Acceleration seemed physically unmotivated, theoretically inelegant, and observationally irrelevant. It was not on the list of things to look for. Then the supernova teams looked for it, not looking for acceleration but using supernovae to measure the deceleration rate, and found it anyway. The method they used is worth understanding, because it illustrates both the ingenuity and the precision required to do cosmology at the frontier. Type Ia supernovae are explosions of white dwarf stars. A white dwarf is the dense, Earth-sized remnant of a star that has exhausted its nuclear fuel. If a white dwarf acquires mass from a companion star until it reaches a critical threshold, known as the Chandrasekhar limit, it explodes in a spectacular thermonuclear runaway. This explosion is extremely bright, bright enough to outshine an entire galaxy for a few weeks. And it has a characteristic pattern of brightening and fading that allows its peak luminosity to be precisely calibrated. Because the peak luminosity can be calibrated, type Ia supernovae are standard candles. If you know how bright something truly is, and you can measure how bright it appears, you can calculate how far away it is. The farther away the supernova, the fainter it appears. This is exactly the same principle that lets you estimate the distance to a streetlight by how dim it looks. The mathematics of how brightness falls off with distance is well understood. And so by observing type Ia supernovae at known redshifts, by combining the distance from the apparent brightness with the velocity from the redshift, the supernova teams could trace the expansion history of the universe. What they found was that the distant supernovae, the ones at high redshift, the ones whose light had been traveling for billions of years, were dimmer than expected. Not dramatically dimmer. Subtly, persistently, reproducibly dimmer. About 20% dimmer than the models predicted. And this dimness had a precise interpretation. The supernovae were farther away than they should be, given their redshifts. The universe had been expanding more slowly in the past than it is today. The expansion was not decelerating. It was accelerating. The universe was rushing apart faster and faster. Both teams reached the same conclusion independently. The systematic errors were carefully checked and rechecked. Alternative explanations, like dust absorbing the light and making the supernovae appear dimmer, were considered and ruled out. The signal was real. The universe is accelerating. When the results were announced in early 1998, the reaction in the physics community was a mixture of astonishment and rapidly growing excitement. Because physicists knew immediately what an accelerating expansion required. It required a form of energy with negative pressure. It required something like the vacuum energy. It required, in Einstein's language, a positive cosmological constant. The thing Einstein had introduced and then discarded was back, and not as a theoretical convenience but as an observational necessity. Since 1998, the evidence for accelerating expansion has been confirmed by multiple independent lines of observation. The cosmic microwave background, the faint afterglow of the Big Bang that fills the entire sky, carries information about the geometry and content of the universe. Its detailed pattern of temperature fluctuations is sensitive to the amount of dark energy, and the measurements are consistent with the supernova results. The large-scale distribution of galaxies, the way they cluster together and form filaments and voids, is also sensitive to the expansion history, and again the measurements point to the same conclusion. Gravitational lensing, the bending of light by massive structures, provides yet another independent probe of the dark energy. All roads lead to the same destination. The universe is about 68% dark energy. And the dark energy is driving an accelerating expansion that will continue indefinitely into the future. What does this acceleration mean for the universe we live in? The implications unfold on several timescales, and they are worth thinking through carefully. On the shortest timescale, which is to say, over the next few billion years, the acceleration has no direct effect on our local environment. The Milky Way, the local group of galaxies, and the nearby clusters are all gravitationally bound to each other. Their mutual gravity is strong enough to hold them together even against the accelerating expansion. We will not be separated from Andromeda by dark energy. Andromeda will still collide with the Milky Way in a few billion years, as planned, entirely unimpeded by the cosmological constant. But beyond the local group, the acceleration is already at work. Distant galaxy clusters are receding from us faster than they used to. The rate of recession increases with distance, so that sufficiently distant galaxies are already receding faster than light, not because they are moving through space faster than light, which relativity forbids, but because the space between us and them is expanding so rapidly that the effective recession speed exceeds the speed of light. These galaxies are already beyond our cosmic event horizon. Their light, emitted today, will never reach us. We can see their past because the light they emitted billions of years ago is still arriving, but their present and future are forever cut off from us. As time goes on and the acceleration continues, the event horizon will sweep inward. Galaxies that are currently just within the observable universe will eventually pass beyond the horizon. The universe we can see will shrink, not in physical size, because the universe is growing, but in the number of galaxies accessible to our observation. In a few trillion years, assuming the current acceleration continues, the only galaxies visible to any observer in our local group will be the galaxies of the local group itself. The rest of the universe, the hundreds of billions of galaxies that we can currently observe, will have been carried beyond the horizon. Future astronomers, if any exist, will look out at a much darker sky. There is something profound about this. The universe is not just a static collection of things waiting to be observed. It is a dynamically changing stage on which the act of observation itself is changing. What is observable today will not be observable tomorrow on cosmic timescales. The knowledge that is available to us right now, the ability to see a universe filled with billions of galaxies and to trace its history back to the Big Bang, is a feature of this particular epoch. We live in a golden age of cosmological observation, and dark energy, the accelerating expansion, is slowly but inexorably bringing that age to a close. On even longer timescales, the acceleration leads to the heat-death scenario. Stars burn out over hundreds of billions to trillions of years. The last red dwarf stars, the dimmest and most long-lived, will exhaust their fuel after perhaps 100 trillion years. After that, the universe will be populated only by stellar remnants, white dwarfs, neutron stars, and black holes. Over vastly longer timescales, the black holes themselves will evaporate through Hawking radiation, leaving nothing but a diffuse gas of photons and neutrinos, cooling and thinning as the universe expands. And through all of this, the dark energy remains. Constant, uniform, filling every cubic centimeter of space with its tiny but inexhaustible energy density. In the very far future, the universe may consist of nothing but an exponentially expanding space filled with dark energy and a thin scattering of radiation that grows thinner with every passing moment. The vacuum energy will be the last form of energy left. The ground state of reality, humming quietly in the darkness, long after everything else has faded. This is a strange destiny, and it is strange in a particular way. It is a destiny dominated not by matter, not by radiation, not by any of the energetic, dynamic forms of energy that produce stars and galaxies and life, but by the vacuum energy, by the energy of nothing, by the irreducible hum of the quantum fields in their ground state. A local minimum is a state that is stable against small perturbations. If you are in a local minimum and you push the field slightly, it will return to the local minimum, just as a ball at the bottom of a valley will return to the bottom if you give it a small push. But a local minimum is not necessarily the true ground state, the global minimum. There might be a deeper valley elsewhere in the energy landscape, a state with even lower energy. If the system is in a local minimum that is not the global minimum, we say it is in a metastable state. It is stable against small perturbations, but not absolutely stable. Given enough energy, or given enough time, or through quantum tunneling, it could transition to the true ground state, the global minimum. This distinction between local minima and the global minimum is absolutely central to the concept of vacuum decay. But before we get there, let us think about how the vacuum state of our universe was established in the first place. The very early universe was hot. Extraordinarily hot. In the first fractions of a second after the Big Bang, the temperature was so high that all the fundamental symmetries of nature were intact. The fields that fill space were not in their current vacuum state. They were in a symmetric, high-energy configuration. As the universe expanded and cooled, these fields underwent what physicists call phase transitions, sudden changes in their configuration as the temperature dropped below critical thresholds. You are familiar with phase transitions in ordinary matter. When water cools below 0 degrees Celsius, it freezes into ice. When water heats above 100 degrees, it evaporates into steam. These transitions involve a reorganization of the system from one state to another, often accompanied by the release of energy, and often involving the breaking of symmetry. Liquid water looks the same in every direction, but ice crystals have a preferred orientation. The freezing of water breaks the rotational symmetry of the liquid state. In the early universe, something analogous happened with the quantum fields. As the temperature dropped, the fields underwent phase transitions, settling into lower and lower energy configurations. One of the most important of these transitions involved the Higgs field. The Higgs field is a quantum field that fills all of space and plays a crucial role in the standard model of particle physics. Its vacuum value, the value it takes throughout space in the current vacuum state, is not zero. The Higgs field has what physicists call a non-zero vacuum expectation value. And this non-zero value is what gives particles their mass. The interaction between the Higgs field and other particles, like electrons and quarks, through their coupling to the Higgs field, is what gives them the inertia we experience as mass. If the Higgs field were in a different vacuum state, with a different vacuum expectation value, the masses of all the fundamental particles would be different. The chemistry of atoms would change. The nuclear reactions that power stars would change. The universe, quite literally, would be a different place. In the very early universe, when the temperature was above a critical value, the Higgs field was in a symmetric state with zero vacuum expectation value. All particles were massless. The fundamental forces that we distinguish today, electromagnetism and the weak nuclear force, were unified into a single force. Then, as the universe cooled below the critical temperature, the Higgs field underwent a phase transition. It fell into a state of non-zero vacuum expectation value. Symmetry was broken, particles acquired mass, the forces separated, and the universe as we know it emerged. This process, the Higgs field rolling from the symmetric state into the broken symmetry state, is sometimes called electroweak symmetry breaking. It happened in the first trillionth of a second after the Big Bang, and it established one of the key properties of the vacuum we currently inhabit. But here is the question that makes physicists nervous. Is the state the Higgs field settled into actually the true ground state, the global minimum of its energy? Or is it just a local minimum, a metastable state that appears stable from the inside but that might, in principle, transition to a state of even lower energy? This question is not merely academic. The answer depends on the precise values of the Higgs mass and the top quark mass, two of the parameters of the Standard Model. These parameters have been measured, most precisely after the discovery of the Higgs boson at the Large Hadron Collider in 2012. And when physicists plug the measured values into the theoretical calculations, they find something that is, to put it mildly, thought-provoking. The calculations suggest that our vacuum is not in the global minimum of the Higgs potential. It is in a local minimum, a metastable state. The true ground state, the global minimum, appears to be at a much higher value of the Higgs field, a state so different from our current state that the physical laws in that state would be completely different. Atoms as we know them would not exist. Chemistry would not exist. Life, in any form we can conceive of, would not exist. The calculations further suggest that our current vacuum, this metastable local minimum, is separated from the true ground state by an energy barrier. To transition from our vacuum to the true ground state, the Higgs field would have to tunnel through this barrier, a quantum mechanical process that we will explore in the next part of our journey. And the timescale for this tunneling, the expected lifetime of our metastable vacuum, is calculated to be much longer than the current age of the universe, possibly much, much longer. This is simultaneously reassuring and unsettling. Reassuring because the lifetime of our vacuum, even if it is finite, appears to be enormously long. Whatever the time scale, it is not something that will happen tomorrow, or in any year with a finite number of digits that you could write down. Unsettling because it means our vacuum is not the ultimate ground state of the universe. We live in a local minimum, a stable-looking but not absolutely stable state. Our physical reality, the laws of physics that govern every atom in our bodies, rests on a foundation that is, in a precise technical sense, not the most stable possible foundation. The universe chose this vacuum state, or found itself in it, through the accidents of the early universe's cooling. The Higgs field, rolling down the energy landscape as the universe cooled, found the local minimum first. It settled there. And the universe that grew from that settling is the universe we inhabit. The particles with the masses they have, the forces with the strengths they have, the chemistry that makes molecules, the physics that makes stars, the biology that makes life. All of it built on a vacuum state that, by the best current calculations, is not the lowest rung of the energy ladder. This should prompt a kind of philosophical vertigo. Everything you know, everything you are, rests on a configuration of fields that is not, in an absolute sense, the most stable possible configuration. It is merely the most stable configuration that the universe found in the fractions of a second after the Big Bang when the Higgs field was settling into place. It is a local optimum, not a global one. A comfortable valley on the way down to an even deeper valley that the universe has not yet found. But there is also something beautiful in this. The fact that our vacuum is a local minimum, rather than the absolute ground state, is part of why it has the properties it does. If the universe were in the absolute ground state, in the deepest possible valley of the energy landscape, the physical laws might be very different. The Higgs field value might be very different. The masses of particles might be very different. And in that deepest ground state, the conditions for atoms, for stars, for life might not exist. We are here, thinking these thoughts, precisely because the universe found this local minimum, this comfortable valley with its particular set of physical laws, and settled there instead of tumbling all the way to the bottom. The vacuum state we inhabit is not the lowest possible energy state, but it is the energy state in which we exist. And that, in a very real sense, is everything. In the next part of our journey, we will explore this concept of metastability in more depth. We will think about what it means to live in a local minimum. We will explore the energy barrier that separates our vacuum from the true ground state. And we will begin to ask the question that lies at the heart of the most dramatic prediction in all of physics. What would happen if the universe tunneled through that barrier? Imagine a landscape, not the flat plains or the rolling hills of the ordinary countryside, but something more dramatic. A landscape with deep valleys and high peaks, with ledges and plateaus partway up the slopes, with some flat spots that seem like safe resting places until you notice the precipice just beyond them. Now imagine that you are sitting on one of those ledges, a wide flat shelf of rock partway up a mountainside. Below you, a sheer drop to a much lower valley, Above you, the mountain continues to higher elevations. You are safe, at least for now. The shelf is wide. The ground beneath you is solid. Nothing about your immediate environment suggests any danger. But you are not at the bottom. You are partway down on a ledge, and below the ledge is a much deeper resting place that you have not yet reached. This is an image of metastability, and it is, according to the best current understanding of particle physics, a surprisingly accurate description of the situation of the entire universe. Metastability is a concept that appears throughout physics, chemistry, and even everyday life. A metastable system is one that is stable against small disturbances but not against large ones. It is in a local minimum of its energy, a state from which small pushes will return it to where it started, but from which a sufficiently large push will cause it to tumble to a lower and more stable state. The classic everyday example is supercooled water. Under the right conditions, you can cool liquid water below 0 degrees Celsius without it freezing. The water is in a metastable state. It should be ice by all thermodynamic reasoning. Ice is the lower energy state at temperatures below freezing. But the water has not frozen because freezing requires the formation of ice crystals, which requires a nucleation site, a tiny seed around which the ice can begin to form. Without a nucleation site, the water remains liquid. It is in a local minimum, not the true minimum. But if you drop a tiny ice crystal into the supercooled water, or tap the container sharply, or introduce any small disturbance that acts as a nucleation site, the water will freeze almost instantaneously. The metastable state will collapse to the true stable state, and the energy difference between the two states will be released as heat. This transition, from a metastable state to a more stable state, is precisely what physicists call a phase transition. And the possibility that the vacuum of our universe is metastable means that our universe might be in a situation analogous to supercooled water. We are in a local minimum. We are stable against small perturbations. But somewhere beyond an energy barrier, there is a deeper state, a true minimum, to which the universe might transition if given the right kind of nudge. The energy landscape of the vacuum, specifically the energy landscape of the Higgs field, is what determines whether our vacuum is stable or metastable. The Higgs field, as we discussed in the previous part of our journey, fills all of space and has a vacuum expectation value that determines the masses of particles. The energy of the Higgs field depends on its value, and this dependence traces out a curve called the Higgs potential. The shape of this potential determines the vacuum structure. In the simplest version of the story, the Higgs potential has two parts. At low values of the Higgs field, there is the electroweak vacuum, the state we currently inhabit, where the Higgs field has its measured vacuum expectation value and the particles have their measured masses. At very high values of the Higgs field, far beyond anything accessible in any experiment, the potential may have another minimum, a deeper valley. Between the two valleys is a barrier, an energy hill that the field must climb or tunnel through to get from one valley to the other. The question of whether our vacuum is stable or metastable depends on the precise shape of this potential, which in turn depends on the precise values of the Higgs mass and the top quark mass. The metastability of the vacuum is invisible from the inside. It cannot be detected by any experiment, any measurement, any observation that we can currently perform. It is a feature of the global energy landscape, not of the local physics. And this invisibility is, in a strange way, comforting. It means that whether our vacuum is stable or metastable makes no practical difference to everyday life. or to any physics we can currently probe. The ledge is wide. The ground beneath us is solid. The danger, if it exists at all, is in the precipice beyond the edge, far from where we are standing. And yet knowing it might be there changes something. Not the physics, not the practical reality of the situation, but the philosophical texture of it. We are not, perhaps, on the most solid possible ground. The universe chose this local minimum, this comfortable ledge, in the cooling aftermath of the Big Bang. And the universe, through quantum processes, could in principle find its way off the ledge to a lower state. The probability is extraordinarily small. The time scale is almost certainly vastly longer than the age of the universe. But in principle, the ledge has an edge. To live in a metastable universe is to live with a kind of ultimate uncertainty, one that operates on timescales so long that it has no practical relevance, and yet one that touches the deepest questions about the nature and the permanence of physical law. Are the laws of physics we observe truly fundamental, or are they accidents of the particular vacuum state the universe found itself in? Could the constants of nature be different, have been different, might one day be different, not because something external changed them, but because the vacuum itself transitions to a new state? These questions do not have answers that we can currently verify, but they are real questions, posed by real physics, arising from real calculations. And sitting with them, allowing them to expand the sense of how contingent and how remarkable our particular universe is, can be its own form of insight. We are on a hillside. It is a beautiful, stable, hospitable hillside. Life flourishes here. Stars shine here. The physics that governs everything we know and love and are emerged here. But it is a hillside, not a valley floor. And somewhere below us, across a barrier we cannot cross easily, there is a deeper place. A place the universe has not yet found. A place with different rules and different physics and a different kind of silence. That place, and the process by which the universe might one day transition to it, is what we explore next. There are ideas in physics that are intellectually beautiful, mathematically precise, and profoundly, carefully, serenely terrifying. Vacuum decay is one of them. It is not terrifying in the way of a monster, or a disaster, or a threat that can be prepared for or avoided. It is terrifying in a much quieter way, in the way that an idea can be terrifying when it reveals something about the deepest structure of reality that changes how you think about the permanence of everything. But here, before we go a single step further, a necessary word of reassurance. The probability that vacuum decay will occur in any time frame relevant to human existence, or to the existence of any stars, or to the existence of the universe as we know it for billions of years to come, is, by all calculations, extraordinarily small. This is not a threat. It is an idea. A remarkable, illuminating, philosophically profound idea about the nature of the vacuum and the contingency of physical law. And it is worth understanding precisely because it is so revealing about the deepest structure of reality. With that reassurance in place, let us go gently into the idea. Vacuum decay is the process by which a metastable vacuum, the kind of local minimum we discussed in the previous part of our journey, transitions to the true ground state through quantum tunneling. It begins, in the theoretical description first worked out by Sidney Coleman and Frank DeLucia in the late 1970s, with a fluctuation. Not a large fluctuation, not a dramatic event, but a small, quantum mechanical, random fluctuation in the value of the Higgs field in some tiny region of space. Normally, such fluctuations occur constantly throughout the vacuum. The quantum fields are always jittering, always fluctuating, always borrowing energy for brief moments and returning it. Most fluctuations are small and return the field to its original value almost immediately. But occasionally, with a probability that can be calculated, a fluctuation will be large enough to push the Higgs field through the energy barrier and into the region of the deeper minimum. When this happens in a small but finite region of space, a bubble forms. A bubble in which the Higgs field has the value of the true ground state, surrounded by the rest of the universe where the Higgs field still has its current value. This bubble has a surface, a thin wall where the Higgs field transitions from the true vacuum value on the inside to the false vacuum value on the outside. And this wall is under enormous pressure. The interior of the bubble, the true vacuum, has lower energy than the exterior. The energy difference drives the wall outward. The bubble expands. It does not expand slowly, not like a soap bubble growing as you blow air into it. It expands at very nearly the speed of light, driven by the energy difference between the two vacuum states. Essentially instantaneously, on any human or even astronomical timescale, the bubble grows from a microscopic fluctuation to an enormous expanding sphere, sweeping outward in all directions, converting the false vacuum into the true vacuum as it goes. And inside the bubble, everything is different. The Higgs field has a different value. The masses of particles are different. The electromagnetic force has a different strength. The nuclear forces have different properties. The chemistry of atoms is different, or perhaps impossible altogether. The physics that allows stars to form, that allows molecules to exist, that allows any structure more complex than a bare quantum field might simply not apply. The true vacuum might be a state in which the complexity we call reality cannot exist. The bubble wall arrives at the speed of light. There is no warning. There is no precursor that propagates ahead of it. There is no signal of any kind that could travel faster than the bubble wall itself. From the perspective of anything in the path of the expanding bubble, there is nothing, and then there is the new vacuum. The transition is instantaneous and total. The physical laws that govern every atom, every force, every interaction are replaced by different physical laws. This is not an explosion in the ordinary sense. An explosion releases energy and sends matter outward but leaves the underlying physics unchanged. Vacuum decay changes the physics itself. It does not destroy structures by applying force to them. It replaces the vacuum state that makes those structures possible. The distinction between the two is profound. An explosion is something happening within the rules of physics. Vacuum decay is something happening to the rules themselves. Coleman and DeLucia worked out the detailed mathematics of this process, and their calculations showed that the rate of vacuum decay, the probability per unit volume per unit time of a bubble nucleating, depends exponentially on the height and width of the energy barrier between the false vacuum and the true vacuum. A high, wide barrier means an exponentially small tunneling probability. And the calculations suggest that if our vacuum is metastable, the barrier is very high and very wide indeed, leading to a decay rate so small that the expected lifetime of our vacuum is vastly longer than the current age of the universe. Some estimates place the vacuum lifetime at numbers with hundreds of digits, timescales so long that they make the current age of the universe, nearly 14 billion years, look like a brief opening flash. But there is an important caveat. The decay rate calculation depends on the detailed shape of the Higgs potential at very high energies, and this depends on aspects of the physics that we do not yet know. If there is new physics beyond the standard model, new particles or interactions that become relevant at high energies, the Higgs potential could be modified. It could become more stable, raising the barrier and extending the vacuum lifetime. Or it could become less stable, lowering the barrier and shortening the lifetime. Without knowing the full theory of physics at high energies, we cannot be certain of the vacuum stability or the decay rate. The discovery of the Higgs boson in 2012 and the measurement of its mass provided crucial input for these calculations. And as we noted, the measured values suggest metastability, but the calculation requires extrapolating the known physics to energies far beyond the reach of any accelerator we have built or plan to build. It requires trusting that the standard model is complete, or at least adequate, up to those energies. This is a significant assumption. Most physicists believe that the standard model is not complete, that there is new physics waiting to be discovered at higher energies. And if that new physics stabilizes the Higgs potential, the entire vacuum stability question may look different. There is another aspect of the vacuum decay story that deserves careful attention. Coleman and DeLucia showed that the expanding vacuum bubble, in a universe with a positive cosmological constant like ours, does something very specific to the geometry of spacetime inside it. The spacetime inside the bubble is not flat Minkowski space, the ordinary flat spacetime of special relativity. It is anti-de Sitter space, a spacetime with negative curvature, like a saddle. An anti-de Sitter space, in the context of a bubble expanding through our universe, would be a region that expands internally but is bounded by the bubble wall expanding outward. The internal geometry is profoundly different from the geometry outside, and the physics inside is profoundly different. All of this happens instantaneously, from the outside perspective, as the bubble wall sweeps through at the speed of light. There is no time for adaptation, no gradual change, no warning. The only process, from start to finish, is the expansion of the bubble wall. It is worth asking, very carefully and very honestly, whether any of this should concern us. The answer, considered with equal care and honesty, is essentially no. Not because the possibility is not real, but because the timescales involved are so vast as to be practically irrelevant. The expected lifetime of our vacuum, if it is metastable, is almost certainly many orders of magnitude longer than the current age of the universe. The probability that vacuum decay will occur in the next billion years, or the next trillion years, is for all practical purposes zero. Stars will form and die. Galaxies will merge and evolve. Civilizations will rise and fall many times over long before any vacuum decay event becomes likely. Furthermore, if vacuum decay were to occur, it would be instantaneous and total. There would be no suffering, no prolonged ending, no gradual deterioration. The bubble wall arrives at the speed of light, and any physical process governed by the current vacuum law simply ceases to apply. This is not something that can be prepared for or mitigated. It is not a threat in any practical sense. It is simply a feature of the universe's deepest structure, a consequence of living in a metastable vacuum, a reminder that physical law is not an absolute and eternal given, but a property of the particular ground state the universe occupies. The value of thinking about vacuum decay is not in the practical implications, which are non-existent on any human timescale. The value is in what it reveals about the nature of the vacuum and the contingency of physical law. The fact that our laws of physics might be the laws of a local minimum, rather than the laws of the absolute ground state, is one of the most philosophically startling implications of modern physics. It means that the rules of the game, the fundamental constants, the masses of particles, the strengths of forces, might all be different in a deeper vacuum. Not different in the way they differ from one place to another in our universe, which they do not, but different in the way that the rules of a different game are different from the rules of this one. This is the fragility of reality that we will explore in the next part of our journey. Not a practical fragility, not a danger to be feared, but a philosophical fragility. The recognition that everything we know, the particles and forces and laws that make up our universe, exists within a particular configuration of the vacuum fields. A configuration that is stable enough to last for timescales that dwarf the current age of the universe. But a configuration that is not, perhaps, the final word. A configuration that the universe found on its way down, and that has lasted long enough for everything we know to come into existence. The bubble of vacuum decay is a thought experiment about the limits of everything, about what it would mean for the substrate of reality itself to change, about the difference between things changing within the laws of physics and the laws of physics themselves changing. And thinking it through, carefully and without panic, is one of the most illuminating exercises in all of physics, because it forces us to ask in the most fundamental way possible what is real, what would remain if the vacuum changed, what is independent of the particular ground state we inhabit, and what does it mean that we are here, thinking these thoughts in this particular vacuum with these particular laws on this particular hillside. These questions do not have complete answers. But asking them, sitting with them in the quiet of this evening, is an act of genuine philosophical and scientific courage, and it opens naturally into the deepest question of all. What would it mean for the vacuum to change? What is actually at stake in the laws of physics themselves? That is where we go next. There is a thought experiment that physicists sometimes use when they want to make the abstract concrete, when they want to take the mathematical formalism of vacuum decay and ask what it would actually mean in experiential terms. Not in the sense of something to fear. We have already established that the timescales involved are practically infinite, but in the sense of understanding what the process would be like if it were to occur. What would it look like? What would it feel like from the perspective of the universe? What would it mean at the deepest level for physical law itself to change? These questions have answers, strange and illuminating answers, and sitting with them can deepen our understanding of what the vacuum is and what our physical reality actually rests upon. Let us build the picture step by step, starting from the beginning of the event as it would unfold in cosmic terms. It starts with nothing visible. No precursor, no signal, no observable warning of any kind. Somewhere in the universe, in some region of space that might be separated from us by billions of light years, a quantum fluctuation in the Higgs field happens to push the field value above the energy barrier. This is not a large event. The initial fluctuation occurs in a region perhaps unimaginably small, perhaps at the Planck scale, the smallest meaningful length in physics, a single point in practical terms. There is no flash of light, no explosion, no observable signature, just a quantum fluctuation that crossed a threshold. Almost immediately, the bubble forms. The Higgs field in that tiny region has tunneled to the true vacuum value. The energy difference between the true vacuum inside and the false vacuum outside drives the bubble wall outward, and the wall moves at very nearly the speed of light. Within a fraction of a second, a bubble that started at subatomic scales has grown to fill a region many light years across. Within a year, a sphere hundreds of light years in radius. The expansion does not slow down. It does not encounter resistance. The physical laws that would resist the expansion, the laws that hold matter together, the nuclear forces that bind atomic nuclei, the electromagnetic forces that hold molecules, these laws are based on the old vacuum. As the bubble wall sweeps through, it replaces the old vacuum with the new. The forces change, the laws change, and whatever was there before simply ceases to be governed by the rules that held it together. From a vantage point extremely far away, outside the future light cone of the nucleation event, nothing unusual would be observed. Light from the regions consumed by the bubble would stop arriving, but this would be indistinguishable from simply running out of light sources. The bubble wall itself would be traveling at essentially the speed of light, so no electromagnetic signal, no light, no radio wave, no information of any kind could propagate ahead of it to provide a warning. The bubble is its own announcement. It arrives when it arrives and not before. From the perspective of anything in the path of the bubble, the experience would be, in the most literal and complete sense, nothing. Not a dramatic explosion, not a flash of light, not a sensation of any kind. The bubble wall is a transition in the vacuum state, a change in the physical laws. Any physical process, any atom, any interaction, any event that was occurring according to the old vacuum laws would simply not continue to occur according to those laws, because those laws no longer apply within the bubble. Everything that the old vacuum made possible would transition instantaneously into whatever the new vacuum permits. What would the new vacuum permit? This depends on the details of the true ground state of the Higgs potential, which we do not know with certainty. But if the true vacuum has very different values for the fundamental constants, as the calculations suggest, then the consequences would be total. The masses of particles would be different. The strength of the electromagnetic force would be different. The nuclear binding energy that holds atomic nuclei together might be zero or negative, meaning nuclei would instantly disintegrate. Electrons might not bind to nuclei to form atoms at all. Chemistry, in any form, would be impossible. The universe inside the bubble would be a place where none of the structures we know, from molecules to cells to stars, could exist. This is not a destruction in the ordinary sense. An explosion destroys by applying force. A fire destroys by applying heat and chemical reactions. These processes operate within the laws of physics. Vacuum decay operates on the laws themselves. It does not destroy atoms by blowing them apart. It removes the physics that makes atoms possible. The distinction is as fundamental as any distinction in science. There is a specific and haunting aspect of the vacuum bubble geometry that Coleman and DeLucia worked out. The spacetime inside the bubble, as we mentioned in the previous part, has negative spatial curvature. It is not the flat spacetime of our everyday experience. It is a hyperbolic space, expanding in a specific geometric way. And this expansion is such that observers inside the bubble, if any could exist, would find themselves in a universe that is rapidly cooling and expanding, heading toward an empty and cold end on a very short timescale. The interior of the bubble is not a new paradise with different but habitable physics. It is a geometry that rapidly evolves toward emptiness. Interestingly, the observers outside the bubble, in the regions not yet reached by the wall, would never know that the decay had occurred. The bubble is expanding at the speed of light. No signal, no light, no information of any kind can escape from inside the bubble to warn those outside. This means that from the perspective of anyone in our universe who is not yet within the expanding bubble, the universe looks completely normal right up until the moment the wall arrives. There is no cosmic news bulletin. There is no advance warning. The vacuum decays somewhere, and the bubble expands, and the wall arrives, and the old laws apply until the very last moment, and then they do not. This thought experiment makes vivid something that is easy to state abstractly but difficult to truly feel. The laws of physics that we rely on, that we take as given, that underlie every scientific experiment and every technological achievement and every biological process, are properties of the vacuum state. They are not independent eternal truths. They are the rules that apply in this particular local minimum. A different vacuum would have different rules, and the transition from one to the other requires no cause, no trigger, no external agent. It requires only time and probability and the irreducible quantum nature of the fields. This is the fragility of physical law, not fragility in the sense of being easily broken. The vacuum is extraordinarily stable and the timescales are enormously long, but fragility in the sense of contingency. The laws of physics, as we know them, are contingent on the vacuum state we inhabit. They are what they are because the Higgs field settled into this particular local minimum in the early universe. They could, in principle, be otherwise. They might, in a different vacuum, support a completely different kind of universe, or no universe at all, in any sense we could recognize. There is a strange comfort available in this perspective, if you let it develop. The fact that vacuum decay is possible but has not happened, at least not in our observable universe and not in the billions of years since the Big Bang, tells us something. It tells us that our vacuum is stable enough, that the barrier is high enough, that the decay rate is small enough, that the universe has had time to evolve into something as complex and rich as what we observe. The stars formed. The heavy elements were forged in stellar cores. The solar system coalesced. Life emerged. Consciousness arose. All of this happened because the vacuum held, because the local minimum is stable enough to last for at least 14 billion years. And it is continuing to hold. Right now, as you listen to these words, the Higgs field has the value it has throughout all of observable space. The laws of physics are what they are. Atoms are stable, chemistry works, life is possible, the vacuum is holding. The bubble has not formed, not here, not yet, not by any reasonable calculation, for an enormously long time to come. And in that ordinary, quiet, unremarkable stability is contained something extraordinary. The entire history of the universe, 14 billion years of stars and galaxies and chemistry and biology, is a story that took place in the space between the formation of this vacuum and its eventual decay. We are living inside a bubble of stable physics, in the best possible sense of the word, a region where the local minimum has held long enough for everything we know to come into being. That is worth pausing to appreciate. Not with anxiety about what might happen in the unimaginably distant future, but with gratitude for what is happening right now. The vacuum is holding. The laws are stable. The physics that makes you possible is operating exactly as it should, and it will continue to do so for longer than the human mind can meaningfully contemplate. Vacuum decay is an idea that, if approached without the proper context, can seem alarming. But approached with understanding, it is one of the most beautiful and illuminating ideas in physics. It reveals the contingency of physical law. It shows the depth of the connection between the vacuum and the structure of reality. It demonstrates that the ground of existence is not an absolute, eternal, unchangeable given, but a dynamic, quantum mechanical, probabilistic state. And it leaves us, paradoxically, with a deeper appreciation for the astonishing stability of the vacuum we inhabit. The bubble has not formed here. And that silence, that ordinary, unremarkable, beautiful silence of a stable vacuum is everything. There is a question that children sometimes ask, and that adults sometimes dismiss too quickly as naive. Why are the laws of physics the way they are? Why does gravity pull with this particular strength? Why does light travel at this particular speed? Why is the universe governed by these particular rules and not some other rules? These questions are often met with a gentle deflection. That is simply how things are. We describe what we observe. Science explains the how, not the why. The laws of physics are what they are because that is what they are. But modern physics, and specifically the theory of the vacuum that we have been exploring throughout this journey, suggests that this deflection, while practical, is not quite honest. It suggests that the laws of physics, at least some of them, are not eternal and absolute truths written into the structure of reality from the outside. They are properties of the vacuum state. They are what they are because the Higgs field and other fields have the values they have in the particular local minimum our universe occupies. And if those field values were different, the laws would be different. The laws of physics have, in a real and calculable sense, a degree of contingency. They might have been otherwise. And in thinking carefully about what that means, we arrive at one of the deepest and most humbling insights that modern physics has to offer. Let us be specific about what we mean when we say the laws of physics are properties of the vacuum state. The vacuum state, as we have discussed, is determined primarily by the value of the Higgs field throughout space. The Higgs field has a non-zero vacuum expectation value in our universe, and this value determines the masses of all the fundamental particles. The electron mass, the quark masses, the W and Z boson masses, all of these arise from the coupling of those particles to the Higgs field, multiplied by the vacuum expectation value. If the vacuum expectation value were different, all these masses would be different. But the mass of the electron is not just a parameter in a formula. It determines the size of atoms. The binding energy of electrons to nuclei depends on the electron mass. Change the electron mass significantly, and atoms either do not form at all, because the electrons are too heavy to be bound in stable orbits, or they form in completely different sizes and configurations. Chemistry, which is ultimately the science of how electron configurations in different atoms interact, would be completely different. The molecules that make up living organisms would not exist in their current forms. Life, as we know it, depends on the electron mass having a value within a very narrow range. Similarly, the quark masses determine the properties of protons and neutrons. The mass difference between the up quark and the down quark, tiny as it is, determines why neutrons are slightly heavier than protons rather than the other way around. This slight mass difference is essential. If neutrons were lighter than protons, protons would decay into neutrons, and atoms of hydrogen, the simplest element, would not be stable. There would be no hydrogen. No hydrogen means no water, no stellar fuel of the most common kind, no organic chemistry, no life. A tiny change in the quark mass parameters, a change of 1% or 2%, and the entire structure of chemistry and biology collapses. The strength of the electromagnetic force determines how tightly electrons are bound to nuclei and how strongly atoms interact with each other. The strength of the strong nuclear force determines how tightly quarks are bound inside protons and neutrons, and how protons and neutrons interact inside atomic nuclei. The strength of the weak nuclear force determines the rate of radioactive decay and the processes that power the sun and produce the heavy elements in stellar explosions. Every one of these force strengths is ultimately determined, in the framework of quantum field theory, by the properties of the vacuum, by the values of the fields in the ground state, by the particular local minimum the universe settled into. This is what physicists mean when they talk about fine-tuning. Not that someone tuned the constants deliberately, but that the constants have values that fall within the narrow ranges compatible with the existence of complex structures. The range of values that would permit atoms to exist, permit stable nuclei, permit chemistry, permit stars to produce heavy elements, permit planets to form, permit life to emerge, is, in the context of the full range of values those constants could in principle take, remarkably narrow. The universe, in this sense, is finely tuned, not by a hand, but by whatever process determined the vacuum state, by whatever physics chose this local minimum out of all the possible minima the energy landscape could contain. There is a philosophical tradition that finds the fine-tuning of physical constants to be evidence for design, for a creator who set the constants at the right values to allow life to exist. This view is taken seriously by some thoughtful people. But physics itself, the physics we have been exploring, suggests a different and perhaps more vertiginous picture. The constants are not externally set. They are properties of the vacuum state, and the vacuum state may be one of many possible vacuum states that the laws of nature, the deeper underlying laws, permit. The deeper underlying laws are the laws of quantum field theory and, ultimately, of whatever theory of quantum gravity turns out to be correct. These deeper laws determine the shape of the energy landscape, the possible vacua, the possible local minima. Within the framework of these deeper laws, many different vacuum states may be possible, each with different particle masses, different force strengths, different physical constants. Our universe, with its particular constants, inhabits one of these vacua. Other possible vacua would give rise to universes with different constants, perhaps no chemistry, perhaps no stable matter, perhaps no spacetime as we understand it. If this picture is correct, then the laws of physics as we know them, the laws that govern everything from atomic structure to the formation of galaxies, are not the fundamental laws. They are the effective laws of our particular vacuum. The fundamental laws are the deeper structure, the energy landscape, the rules that determine which vacua are possible. And the particular effective laws we observe are contingent on which vacuum was selected in the early universe. This picture challenges a deeply held intuition about the nature of physical law. We tend to think of the laws of physics as necessary truths, as features of reality that could not be otherwise. The speed of light, the charge of the electron, the strength of gravity, these feel like fundamental constants of the universe, not contingent facts that could have been different. But if they are properties of the vacuum state, then they are, in a precise sense, contingent. A different vacuum would have different laws. A different universe, governed by different effective constants, is not just imaginable but is, within the framework of modern physics, a real theoretical possibility. This does not make the laws we observe less real or less important. Within our vacuum, the laws are absolute and universal. The speed of light is the same everywhere in our observable universe. The charge of the electron is the same in every atom. These are genuine universals within the scope of our vacuum, but they are not, perhaps, universals of the deepest structure of reality. They are the rules of this game, not the only possible rules. There is something both humbling and liberating in this. Humbling because it suggests that the laws of physics we have spent centuries discovering and systematizing are not the final word, not the deepest truth, but a layer, a beautiful and astonishingly successful layer of something deeper. The laws are real, but they are properties of a state, not properties of the ultimate substrate. Liberating because it opens the possibility of a richer structure beneath the laws, a structure with its own logic and its own beauty, a structure that might eventually be understood. The study of vacuum stability, of phase transitions, of the Higgs potential, is in this sense a study of the foundations of physical law. When we ask whether our vacuum is stable, we are asking whether the laws of physics we observe are permanent features of our universe or temporary features of a particular phase. When we ask what the true ground state looks like, we are asking what the most fundamental layer of the universe's physics is. What kind of effective laws would operate in the deepest possible vacuum? These are not merely technical questions. They are questions about the architecture of reality. And they are questions that modern experiments are beginning to address, however indirectly. The Large Hadron Collider at CERN, by measuring the masses of the Higgs boson and the top quark with increasing precision, is providing better and better input for the calculation of vacuum stability. Future colliders, if they are built, will measure these masses even more precisely. The shape of the Higgs potential at high field values is, in principle, accessible to calculation from these measurements. Whether our vacuum is stable or metastable is a question that experiment, combined with theory, is slowly working toward answering. The fragility of physical law is not something to fear. It is something to appreciate. It tells us that the universe is richer than it appears, that beneath the laws we observe is a deeper structure, that the rules of the game are themselves part of a larger game. It tells us that the questions we ask about physics are not limited to describing what happens within the laws, but extend to asking why these particular laws, why this particular vacuum, why this particular configuration of fields that makes atoms possible, makes stars possible, makes us possible. These are the questions that define the frontier of physics, not questions about specific particles or specific forces, but questions about the vacuum state of the universe, about the energy landscape of the Higgs potential, about the relationship between the effective laws we observe and the deeper structure that generates them. Questions about why the silence has the shape it has, about why the hum of the vacuum has the particular frequency it does, about why the nothing of empty space is organized in the specific way that makes everything possible. These are the deepest questions physics currently faces, and they arise directly from the recognition that empty space is not empty, that the vacuum has structure, that the laws of physics are properties of the ground state. The fragility of physical law is the flip side of the richness of the vacuum, and both are consequences of the same beautiful, strange, endlessly surprising truth. The silence is not nothing. The silence has a shape, and the shape of the silence is the shape of the universe. If the vacuum state of our universe is one local minimum among many possible minima, then a natural question follows almost immediately. Are the other minima occupied? Are there other universes, other regions of reality, governed by different effective physical laws, because they settled into different vacuum states? This question, which might have seemed purely philosophical a few decades ago, has become a serious topic of theoretical physics. It is the question of the multiverse. And while it remains deeply controversial and not yet directly testable, it arises naturally and, in some frameworks, almost inevitably from the same physics that tells us about the vacuum energy and the cosmological constant. Tonight, let us walk gently through this territory, not committing to any particular answer, but exploring what it would mean if other vacuums exist and what kinds of universes they might contain. The starting point is a theoretical framework called eternal inflation. You may be familiar with inflation. the period of extremely rapid exponential expansion that most cosmologists believe occurred in the very early universe, in the first fractions of a second after the Big Bang. Inflation was proposed to solve several puzzles about the large-scale structure of the universe, including why it is so uniform in all directions, why its geometry is so nearly flat, and why it does not contain large numbers of exotic magnetic monopoles that grand unified theories predict should have formed in the hot early universe. Inflation, driven by a hypothetical field called the inflaton, can solve all of these problems by stretching any small initial patch of space to enormously large scales, smoothing out variations and diluting unwanted relics. Eternal inflation is a version of inflation in which the inflationary process, once started, never completely stops. In eternal inflation, the inflaton field is always quantum fluctuating. Most regions inflate and eventually stop inflating, becoming the kind of slowly expanding universe we see around us. But some regions, through quantum fluctuations, continue to inflate. And because inflationary expansion is so fast, those continuing regions grow faster than the regions that stop. The result is an ever-expanding inflationary background, from which bubbles of non-inflationary space continuously nucleate. Each bubble becomes a universe. And the inflationary background produces bubbles forever, without end. In this picture, our entire observable universe, with its hundreds of billions of galaxies and 14 billion-year history, is just one bubble in an infinite foam of bubbles. Each bubble nucleated when the inflaton field in that region transitioned to a lower energy state. Each bubble started with its own Big Bang. Each bubble evolved according to the laws of physics that apply in its particular vacuum state. And each bubble is, in principle, causally disconnected from all the others. No signal can travel between bubbles. Each one is its own isolated universe. Now here is where the connection to the vacuum becomes crucial. In the string theory landscape, the theoretical framework that predicts an enormous number of possible vacuum states, each bubble that nucleates from the eternal inflationary background might land in a different vacuum. The inflaton field, as it transitions to a lower energy state in a given region, might settle into any of the many possible minima of the energy landscape. Different bubbles settle into different minima. Different bubbles have different effective physical constants. Different bubbles have different particle masses, different force strengths, different cosmological constants. In this picture, the multiverse is not just a collection of universes with the same laws of physics. It is a collection of universes, each with its own effective laws of physics, each governed by the particular vacuum state it found itself in when inflation ended. Some of these universes would have physical constants that permit complex structures. Some would not. Most, according to the calculations, would have cosmological constants much larger than ours, meaning they would expand too rapidly for galaxies to form, or collapse too quickly for anything to develop. A small fraction would have cosmological constants in the habitable range. And we, inevitably, find ourselves in one of those. This is the landscape solution to the cosmological constant problem, the anthropic approach we discussed earlier. In a multiverse with an enormous number of possible vacua, all values of the cosmological constant are represented somewhere. We observe the value we observe not because it is fundamental, but because it is the value present in the kind of universe that can contain observers. The other universes, with their different constants, are real, but they are empty of observers to notice their properties. This is an extraordinary idea, and it is worth sitting with it for a moment, not to evaluate whether it is correct. because we do not yet know, but to appreciate what it implies about the concept of the vacuum. If the multiverse picture is right, then the vacuum state of our universe is one of perhaps 10 to the power of 500 possible vacuum states. Each one would be a valid solution to the underlying laws of physics. Each one would support its own effective constants, its own particle masses, its own force strengths. The vacuum we inhabit is not special in any absolute sense. It is simply the one we find ourselves in. What would the other vacuums look like? Most of them, we expect, would be hostile to complexity. Many would have such large vacuum energy that space would expand so fast that no structure could form. Others would have such large negative vacuum energy that the universe would collapse almost immediately. Others would have particle masses so different that stable atoms could not exist. Still others might know stable matter at all, just a sea of fields in their ground state with no excitations that could accumulate into anything. The vast majority of possible universes, if the landscape picture is right, are empty and structureless, just quantum fields in their respective ground states with no chemistry, no stars, no complexity, no observers. But here is something remarkable. Even those empty universes, those sterile vacuums with their hostile constants, are not nothing. They are still filled with the quantum fields of their respective vacuum states. They still have their own version of the zero-point energy. They still have their own version of the vacuum fluctuations. They still have their own irreducible, unavoidable, inescapable quantum activity. The nothing of those universes is still a something. Their silence still breathes, just in ways that do not produce the kinds of complexity we are familiar with. This is a profound point. In every possible vacuum, no matter how sterile and structureless it might appear, the quantum fields are still present. The uncertainty principle still applies. Zero-point energy still exists. The vacuum is never, in any possible universe, truly and absolutely nothing. The nothing is always a something, everywhere, always, in every possible instantiation of the laws of physics. The breathing of the vacuum is not a special feature of our universe. It is a feature of quantum mechanics itself, of the structure of fields and uncertainty that applies wherever those laws hold. The multiverse, if it exists, is not a collection of voids. It is a collection of different somethings, each with its own quantum fields, each with its own vacuum energy, each with its own irreducible hum. The silence in each of these universes is different, tuned to different constants, vibrating at different frequencies, supporting different or perhaps no structures. But the silence is always there. The vacuum always breathes. Nothingness is always alive with the minimum possible activity. There is a question of testability that must be addressed honestly. The multiverse, as currently formulated, is not directly testable. We cannot observe other bubble universes. We cannot compare our constants to those in another bubble. We cannot visit other vacuums. This has led many physicists to question whether the multiverse is a scientific concept at all, or whether it is a philosophical or metaphysical proposal that lies beyond the reach of empirical science. The debate is genuine and important. A scientific theory should, in principle, be testable. If the multiverse cannot be tested, then it is not science in the traditional sense, however intellectually compelling it might be. There are, however, some proposals for indirect tests. In certain versions of eternal inflation, bubble universes can collide, and these collisions would leave signatures in the cosmic microwave background. Searches for such signatures have been conducted and so far have found nothing definitive. Some physicists have proposed that statistical patterns in the distribution of physical constants across the multiverse might leave signatures in the properties of our universe that could, in principle, be detected. These proposals are speculative but not obviously incoherent. What the multiverse picture represents, at minimum, is a remarkable extension of our conception of the vacuum. The vacuum is not just the ground state of our universe. It is one ground state among many possible ground states. The emptiness of our space is one kind of emptiness among many possible kinds. The hum of our vacuum is one particular frequency among many possible frequencies. And this multiplicity, whether or not the other frequencies are actually realized in other universes, tells us something important. There is a question of testability that must be addressed honestly. The multiverse, as currently formulated, is not directly testable. We cannot observe other bubble universes. We cannot compare our constants to those in another bubble. We cannot visit other vacuums. This has led many physicists to question whether the multiverse is a scientific concept at all, or whether it is a philosophical or metaphysical proposal that lies beyond the reach of empirical science. The debate is genuine and important. A scientific theory should, in principle, be testable. If the multiverse cannot be tested, then it is not science in the traditional sense, however intellectually compelling it might be. There are, however, some proposals for indirect tests. In certain versions of eternal inflation, bubble universes can collide, and these collisions would leave signatures in the cosmic microwave background. Searches for such signatures have been conducted and so far have found nothing definitive. Some physicists have proposed that statistical patterns in the distribution of physical constants across the multiverse might leave signatures in the properties of our universe that could, in principle, be detected. These proposals are speculative but not obviously incoherent. What the multiverse picture represents, at minimum, is a remarkable extension of our conception of the vacuum. The vacuum is not just the ground state of our universe. It is one ground state among many possible ground states. The emptiness of our space is one kind of emptiness among many possible kinds. The hum of our vacuum is one particular frequency among many possible frequencies. And this multiplicity, whether or not the other frequencies are actually realized in other universes, tells us something important. It tells us that the vacuum is not a simple, unique, inevitable thing. It is a complex, structured, rich concept with many possible realizations. To think about other vacuums, even hypothetically, is to develop a deeper appreciation for our own. The particular vacuum we inhabit, with its particular constants that allow atoms and chemistry and stars and life, is not the only possible vacuum. It is a special one, in the sense that it is hospitable. In the enormous space of possible vacuum states, it is one of the rare ones where complexity can arise, where the zero-point energy combines with stable structures to produce something more than an empty, structureless sea of fields. We live in a rare vacuum, a hospitable vacuum, a vacuum whose particular silence has exactly the right frequency to allow us to exist and to ask questions about it. That is something worth holding gently, with gratitude and with wonder. Throughout this journey, we have been approaching the vacuum from the direction of physics. We have talked about quantum fields and virtual particles, about zero-point energy and the Casimir effect, about dark energy and vacuum decay. And these scientific concepts have revealed something extraordinary, that the nothing of empty space is not nothing at all, that the vacuum is alive with structure and activity, with invisible fields and transient fluctuations, with energy that shapes the cosmos and holds atoms together. But now, As we move into the quieter reaches of our journey, let us step back from the equations and the measurements and ask a different kind of question. What does it mean, philosophically and experientially, to understand nothingness as a dynamic presence? What changes when we accept that the nothing we thought we knew has been replaced by a something that refuses to be still? The concept of nothing has a long and tangled history in philosophy. The ancient Greeks were among the first to wrestle seriously with it. Parmenides, one of the earliest and most radical of the pre-Socratic philosophers, argued that nothing cannot exist. The very act of thinking about nothing makes it something, because thought requires an object, and an object is something. To say there is nothing is self-defeating, because the saying makes the nothing into a subject of discourse, which is a kind of being. Parmenides concluded that reality is a single, indivisible, unchanging whole, because any change would require something coming from nothing, which he held to be impossible. Aristotle pushed back against this in various ways, but he also resisted the idea of a true void. He argued that empty space was impossible because the properties of a place are always defined by what occupies it. A space with nothing in it would have no properties at all, including no location, no size, no shape, which seemed contradictory. The medieval philosophers inherited this debate and struggled with it in the context of their theological concerns, asking whether God could create a true void, and whether a void would undermine the coherence of the created order. The scientific revolution eventually resolved many of these debates in favor of the void. The invention of the vacuum pump and the demonstration that air could be removed from a sealed vessel showed that, at least physically, a region devoid of air was possible and coherent. The development of classical mechanics and, later, electromagnetism seemed to require the existence of a vacuum through which light and gravity could propagate. The void became a respectable physical concept, even a necessary one, and then quantum mechanics arrived and complicated everything again, not by returning to the ancient Greek position that nothing cannot exist, but by showing that even the most emptied, most cleared, most stripped-down region of space still contains something. The quantum vacuum is not the classical void. It is a physical state with definite properties. It has energy. It has fluctuations. It responds to boundaries and fields. It contributes to the forces between particles. It drives the expansion of the universe. The quantum vacuum is a something, and the old concept of nothing, the classical void, does not appear to exist in nature. This is a remarkable philosophical development. It does not vindicate Parmenides exactly, because the something of the vacuum is not the same as the indivisible, unchanging being that he proposed. But it does suggest that his intuition was pointing at something real. The attempt to construct a true nothing, a truly empty space, fails. Nature resists it. The uncertainty principle prevents it. The zero-point energy remains. The vacuum fluctuates. Nothingness, as a static and complete absence, is not a physical possibility. What we have instead is a dynamic presence masquerading as absence. The quantum vacuum is what remains when you remove everything you can remove. It is the irreducible, unavoidable, minimum state of physical reality. And that minimum state is not zero. It is not still. It is not silent in any absolute sense. It hums. It breathes. It flickers with the ghosts of particles that blink in and out of existence too quickly to be directly caught. It fills all of space with an invisible energy that shapes the cosmos on the largest scales. It is, in the most literal and technical sense possible, a presence. There is a philosophical tradition, found in various forms in Buddhism, in Taoism, and in some strands of Western mysticism, that associates emptiness not with absence but with potentiality. The empty space is understood not as a void but as a ground of possibility, a matrix from which things arise and to which they return. The Buddhist concept of shunyata, often translated as emptiness or voidness, does not mean that things do not exist but that they exist without inherent, fixed, independent essence. They are empty of absolute self-nature but full of relational being. They arise from conditions and return to conditions. The empty is not nothing. It is the open space that makes arising possible. The quantum vacuum is not the same as shunyata. Physics and philosophy operate in different registers, but there is a resonance worth noticing. The quantum vacuum is the ground from which particles arise and to which they return. It is the condition that makes matter and energy possible. It is the state that underlies all other states. And it is, as we now thoroughly established, not empty in any absolute sense. It is full, in its own way, of the minimum possible activity, the irreducible quantum breath. The resonance between the scientific understanding of the vacuum and these philosophical and contemplative traditions is not an accident, and it is not a case of physics confirming religion or philosophy. They are independent lines of inquiry that have arrived, through very different methods, at a similar intuition, that the ground of reality is not inert, that emptiness is not absence, that what appears most empty contains the most fundamental form of presence, that the silence, at the deepest level, is not static but alive. This realization changes something about how the world feels, or at least it can, if you let it. The empty space around you, which ordinary experience treats as nothing, as just the backdrop against which things happen, is revealed by physics to be one of the most fundamental and active participants in physical reality. It is filled with quantum fields. It carries vacuum energy. It supports the virtual particles that mediate the forces between atoms. It is the stage on which the drama of matter plays out, but it is not passive. It contributes. It pushes. It shapes. It participates. The nothing you see when you look at the dark between the stars is not nothing. It is the quantum vacuum, filled with the same fields that fill the space inside your body, carrying the same zero-point energy, participating in the same invisible sea of fluctuations. The darkness between galaxies is not more empty than the space inside an atom. They are both the same quantum vacuum, the same irreducible minimum of physical reality, the same dynamic presence that refuses to be nothing. There is also a deeper philosophical question lurking beneath all of this. Why is there something rather than nothing? This is perhaps the oldest and most fundamental philosophical question, the question that lies at the root of all metaphysics. And the quantum vacuum, interestingly, has something to say about it, though not a complete answer. The quantum vacuum suggests that the question may be misposed. It assumes that nothing is the natural default state of reality, the baseline from which something must be explained. But the quantum vacuum shows that nothing, in any physically realizable sense, is already a something. The simplest possible physical state is not nothing but the vacuum. And the vacuum is not nothing. It has energy. It has fields. It fluctuates. If the vacuum is the closest thing to nothing that physics can construct, and if even the vacuum is a something, then perhaps the question should not be why is there something rather than nothing, but rather, why is there this particular kind of something? This particular configuration of fields in this particular vacuum state, rather than some other kind of something.